Hello, Varun sir. Hello, Varun sir.
Hello.
Yeah, so like with what system you joined, sir? Hello, hello. Yeah, hello, Varun sir. Am I audible to you? Hello, hello, Varun sir. Hello, hello, Varun sir. Am I audible to you? Hello, Varun sir.
Hello.
Yeah, Varun sir.
Hello.
Yeah, hello, sir. Am I audible to you, sir? Varun sir. Sir, am I audible to you? Hello, hello, Varun sir. Yeah, hello, Varun sir. So now am I audible to you? Hello, hello, Varun sir. So we are not able to hear you. Hello. Yeah, hello, Varun sir.
Hello. I don't have Windows with me. Hello.
Yeah, Varun sir.
Yeah, I am able.
Sir, may we know with what system you joined? So again, you are not audible to us.
Good morning. Good morning, Abhinandan, sir.
Good morning, ma'am.
Sir, actually, yesterday night I had a word with Ganeshan, sir, regarding the issue. So, sir, can you please confirm whether Varun, sir, has joined from an Ubuntu system or not? Because in WebEx event, we have one issue regarding this Ubuntu system.
Let me get back to you. Give me a minute.
Sir, can you please confirm us if sir has joined with an Ubuntu system or
Yeah,
not?
I will do that. I will do that.
Yeah, sure. Thank you, sir. Thank you.
And so in case he joined with Ubuntu system, so if you can please ask him to join with any of Windows system, then this problem will get resolved.
No, but he is actually he uses only Ubuntu. So I doubt he might have some Windows machine. Let me talk with him.
Okay, sure, sir. Sure, please.
Ma'am, he is not able to join.
So in that case, what can be the solution, sir?
Okay. So we will work with other presenters so that meantime we can actually start.
Sir, sir, if we can unmute Varun sir, if Varun sir is audible, and if he shares the like slides with you, so will that be possible? So that you can coordinate with Varun sir and can change the slides, and so that Varun sir can speak.
That is fine with me. Let me talk with him.
Yeah, please, sir.
Yeah, Abhinandan sir, Pubali. So actually, just had a word with Ganeshan sir. So sir told me that today we will be having it in the event. So Ishan sir will be joining in few minutes, and then we can, if the same issue is there, then we can schedule the meeting tomorrow in the WebEx meeting. Pubali.
Yeah, ma'am.
Okay.
Yeah, just give me 2 minutes. I'm calling you. Okay.
Sure.
So there is another important announcement for all participants. We have seen in the list that you have joined with numbers and the registered email ID you have not used for joining this event. Yesterday also we made an important announcement. Now also we are making the announcement again. Please join with your registered email ID in the meantime when we are doing our setting, because your registered email ID will be marked, will be used for marking the attendance. No further request will be entertained. So please join by your registered email ID. It is not possible for us to track each and every ID. Please try to understand there are 450 attendees joined. So it is very difficult for us to track the individual numbers. Again, I'm saying that there are few numbers like 19701A042. We will not be able to recognize. So please sign out and join by your registered email ID. It is an important announcement for everyone. Please join by your registered email ID. Otherwise, your attendance will not be marked and no further requests will be entertained. Thank you.
Hello. Feroza ma'am, actually, even Ishan is also using Ubuntu only. Hello.
Yeah. So can you please communicate once with Ishan sir or Varun sir if they share the slides with you and you can coordinate and change the slides for them and they can speak from the
See,
attendee.
Varun's, Varun's is basically a demo. So that's not possible. Ishan's, I can do that. But what he was telling was, can we actually have some Google Meet so that I can share the screen over it, something like that?
So just give us few seconds, sir.
Yeah. Ma'am, can you make Varun as a panelist? Is it possible? He also debugging from his side.
No, sir. We are unable to make him the panelist.
Okay. Ma'am, can you make him as a co-host? Varun as co-host?
Sir, not possible. Abhinandan, sir, can you please share your mobile number in the private chat?
Yes. It's showing only all. Yeah,
So
sent you.
yeah.
Yeah.
Good morning to all the participants. So thank you for joining on time. So what we'll start today's session in another 10 minutes. So we are having some technical issues at experts end. So please wait for another 10 minutes. We'll start the session. Meantime, if any one of you have not joined with your registered email ID, kindly disconnect yourself and join again with registered email ID only. Okay, so kindly get connected, be ready. We will start the session in another 10 minutes. Abhinandan sir, if you can see the message.
I sent to host.
Okay. Yeah. Thank you, sir. Thank you. Hello, Abhinandan sir. Yeah. Sir, we
Yeah,
made you the
the thing is that
presenter.
Ishan was able to get a laptop, so he would be joining in another 5 to 10 minutes. This one for Varun, I would actually coordinate with him to set up some in the some Zoom or Google Meet so that I would present. I would
Yeah.
share the screen.
Okay. So now what we need to do, sir? So will you like be sharing for Varun sir, or Ishan sir will be presenting
No,
now?
Ishan would join so that things would actually work.
Ishan sir. So today's whole session will be taken by Ishan sir.
No, Ishan, Varun, and at one we have Arjun.
Yeah. So Varun sir problem that will be like the same even if Ishan sir joins for now. So that
Yeah,
the for Varun sir we need to resolve this.
yeah. So that let the session start. At least
Yeah.
with Ishan. So meantime, I will have some time with Varun to set up few
Okay.
things.
Sure, sir.
Yeah. So Varun will join because at least Ishan yeah, as PPT, but Varun it is more. It is a it works
Demo.
only on
It will be a
Ubuntu.
demo.
So we don't have any other option. We need to
Okay.
see a workaround. That's it.
Okay.
Okay.
And to all the participants, yesterday, to all the participants, yesterday one Slack channel invite has been sent. Uh, Slack channel invite has been sent in your registered email ID. So I request all of you to kindly join and create an account and join in the Slack channel. So in that group, any queries you are having, related to the topics of the sessions. So you can post your queries in that channel. So please accept the invite and join the Slack channel sent in your email yesterday. Yeah, and regarding your attendance for yesterday's session, we'll share your attendance by today itself. So we'll intimate you once the attendance is done. So we'll let you know all the information regarding your attendance. Hello, Ishan sir.
Yes, ma'am, I'm audible.
Yeah, sir, we have given you the presenter rights. Can you please check if it's if you can share your screen or not? Yes, sir. So your screen is visible. So can you just change the slides so that we can check once? Yeah,
Changing.
it's working. Sir, I guess your voice is little low. So can you speak something for a few seconds?
Yeah, I'll do that. I know I think I'm speaking only softly, so I think it'll be fine now. Is it better?
Yeah. It's okay. Okay. So, sir, like, shall we start?
Yeah, I think we can start off.
Yeah, okay. Thank you, Ishan sir. Thank you, Abhinandan sir. And a very good morning to all the coordinators, and to all the participants joined today. So we'll start with the first session today. So there is just like shuffling of the contents. So we'll start today's session with on the topic microprocessor construction using open power ISA. And this topic will be taken over by Mr. Ishan Singh. Ishan sir is a well-equipped software engineer, competitive programmer, and an experienced web developer with sound knowledge of operating system, COA, and HPC. Apart from being the class representative and the internship coordinator from the for the placement cell at NITK. He has a keen interest and experience with the N-Power ISA as part of his COA course. So with this short introduction of this Ishan sir, I request sir to please start with the session.
Thank you. Thanks for that intro. Good morning, everyone who's present on the call, members of academia, all dignitaries. Welcome to this session. I'm Ishan Singh. I'm not really a sir. I'm just a third-year undergraduate who is undergoing his BTech CSE majors from NITK Surathkal right now. And yeah, so whatever you heard in that intro, all of that stuff is just a byproduct of what I've learned in these 3 years. And what I will be doing today is just share my experience with working on a project. This project was given to me by my professor as an assignment in one of our courses. So that is what I'll be presenting today. Before I start off, let's see a little bit of a background about how this project came about, and before we get into the what and how. So let's see when. So in our first year, we had the generic college stuff, so we learned C programming and stuff. And in the second year, we had a course which was DDS, which was Design of Digital Systems, where we actually learned how to make a circuit, right? How to use Verilog and run simulations, how to write test benches for the Verilog modules that we made. So that happened. Moving on to our previous semester, which was the fourth semester, there we had a course which was COA, or the Computer Organization Architecture course. And in this course, we learned how to break the processor into different parts, right? And these parts are basically your register file unit, your memory hierarchy, and of course, your CPU, the processor itself. So how do you break a processor into these units? Now, this processor which we were studying about was a one-by-one instruction executioner. So what it does was it took up one instruction, executed it to its entirety, then took up a new instruction, executed that, and so on and so forth. So we thought can we make this processor faster, right? Can we increase our CPU utilization? And the answer was yes. And how do you do it? So basically, every instruction takes, let's say, 5 clock cycles to complete. And in these 5 clock cycles, CPU clock cycles is what I'm talking about. And in these 5 clock cycles, different hardware resources are going to be accessed. So that one instruction might be dealing with, let's say, a memory load, right? And when memory load, the actual process is happening, the CPU is actually sitting idle. So the ALU is actually sitting idle. So can there be a way in which we can overlap 2 or more instructions so that they run parallelly on the system, but use different hardware resources, right? And that is when the concept of pipelining was taught to us. Now, there are a lot of issues with pipelining. To start off, one of the issues is that when you have an overlap of instructions, it is very possible in a real life state that 2 or more instructions are trying to access the same piece of hardware at the same time. Let's say 2 of your instructions are trying to write some data object to the register file at the same time, which cannot happen because the register can only accept one value at a time. So these kind of issues can exist, right? And that is when these kind of issues were called stalls. There could be data stalls, data hazards and things, or structural hazards. And the ways to overcome these hazards. It was at this point in time that this assignment was given to me. And the assignment was to use a given ISA whose manual would be provided to us. We had to just build a 5-stage pipeline and just use TL Verilog for this project. That was the thing, right? And we had to write a meaningful program that would run on my ISA implementation. So now, before obviously coming for this session, I asked for the demographic of the audience, and I'm pretty much aware that the guys who have joined the session either know everything that I know or know a little bit more because you guys are technically my seniors. So given that demography, it is not possible that I can teach you something or impart some knowledge, but what I can do is share some experience, right? And just showcase my work. So that is what I'll be doing. So before starting off, I just like to thank all the organizers and specifically Ganeshan sir for giving me this opportunity. So let's start off. Right. So our project, we basically had an ISA manual in front of us. Now what the ISA manual contains is that when you implement an ISA, you will be needing some guidelines. Now these guidelines could be about the instructions in the ISA or used by the ISA. So how are the instructions encoded? What are the fields present in that instruction? Right, these kind of things. Then are there any special register files which are needed? So all of this stuff is going to be present in the ISA manual. So I'll be presenting some parts of the ISA manual and then we'll move on to the other things. Right. Now what was given to us was not exactly the open power ISA. We got a subset of the power version 3.0 ISA. So basically our entire course, which we had done up to that point in time, was based on RISC-V, right? We had done RV64I, which is a subset of the RISC-V instructions, where every data block is 64 bits long and it only dealt with integers. So there were no floating points and things. Also, it was a very basic operation set. So we had only addition, subtraction, the normal AND or NAND NOR, these operations were there, but nothing crazy, right? So it was just the RV64I, the basic subset of the RISC-V ISA. Now, what was given to us here was the N-power ISA, which was completely new for us. But again, since the manual was provided, everything was going to be straightforward. So we're given that. Some points about the ISA were that it was a 64-bit ISA. So again, all our data items are going to be 64 bits long. The instructions are going to be 32 bits long itself, as in the RISC-V ISA. So it is a very simplified ISA compared to what Power is using right now. So all the registers were 64 bits. And they were numbered in the opposite sense. I mean, normally when you see a number which is 64-bit long, the 0th bit is going to be your LSB and the 63rd bit is going to be the MSB. But again, this was inverted. This just coming from the ISA again, for some reason, the instruction set is inverted, which I'm sure you'll get to know why. in the future sessions. But all in all, the ISA specified to us that there were technically 4 kinds of instructions present in the ISA. One were the arithmetic and logical unit expressions. So things like addition, subtraction, and your and, or, and, nor kind of instructions. Then there were the data transfer instructions, which were the loads and stores. Followed by that, there were the compare and branching instructions, so which you would use for loop execution, for example, or even for unconditional branching, or as return statements for your functions, right? So that's where you would use the compare and branching instructions. Then came the shift and rotate instructions. These were basically the kind of instructions we had. These were the classes of instructions. But again, we were dealing with only integers, and we were only dealing with the basic RV64 kind of operations, I kind of operations. So we are not looking at multiplications. We are not looking at floating point units, none of that. So it was a very simplified set of instructions. So all our instructions were going to be again 4 bytes long and going to be word aligned, right? So nothing crazy. It was a simplified ISA. Now, coming to the logical processing model. So this ISA implementation, which we are going to do, was a load and store ISA kind of thing, right? So what a load store ISA does is that your processor does not directly interact with the memory units, right? I mean, it interacts directly, but it cannot make changes to the data directly in those memory locations. The memory has to be first fetched into the register files. Then you perform your operations on the GPR or the general purpose registers. And then that output can be stored onto the register file itself or can be transferred to the memory, right? So it was a very load store ISA. We did not have direct access to memory. So what happened was we used the memory to fetch an instruction. Now that instruction was used up by the GPR file. That was basically the register file, and it only worked on integer data. It produced some output data, which was again stored into the memory, right? And in between, we had to perform a branching check. So that is what we had to do. So this was our model. Again, I think the same things are written here. There were no computational instructions that modified elements directly in memory. To use an operand from memory, so it's the same thing, right? You must have to load the values into the register, modify them there, and then store it back onto the target location. So that was our working model, which we had to implement. Then moving on, what does the register file look like, right? So I told you all the data blocks are going to be 64 bits long. So that is what this is. You see, this is a 64-bit long register, and there were 32 of these, right? So there were 32 64-bit long registers, and that is our register file. So the power ISA, N power ISA, uses instructions that are 4 bytes long and are word aligned. A set of 32 GPRs, each of 64 bits, was available to us, and signed integers were represented in the 2's complement form. Okay, so this was something, again, all of this information is coming from the ISA. I will show you the entire ISA in some time, but this is what it is. Now, the memory layout. What does the memory layout look like? So it's a normal thing that you see in all your operating system courses as well, right? You have some reserved space at the bottom, which would be for error handling, debugging, or just to store some OS specific information. Then you have the text or instruction section where your actual program resides, right? And then associated with that, you have a register called the PC, or the program counter, that tells you which is the next instruction to be executed. Then you have the static data or the global variable section. Finally, you have the heap and stack, the stack that builds downwards and the heap that builds upwards, right? Just the normal picture. And associated with this memory space, you have another pointer, which is the SP, or the stack pointer, which points to the top of the stack, right? So there's your memory layout. Pretty standard stuff, right? Let's move on to the next page, right? Now, the ISA, this is the core of the ISA. It talks about the instructions which are being used. Now, I'm sure you guys have seen the RISC-V ISA instructions. Now, in the N power ISA, the instructions are a bit different, obviously, like the naming is different and the fields are called differently. So you see something called a PO here. This is the primary opcode. Then you have something called the XO, which is the extended opcode. And this PO and XO together decide what exact kind of an operation it is, right? So operations which are similar in nature, for example, the add instruction and the AND instruction are similar in their working, right? In the sense that at the ALU level, they work similarly. So they will have the same PO. Okay. So they'll have the same PO, but they will differ in their XO, right? And the combination of PO and XO together are going to tell you what exact kind of an operation it is. So these were basically the different formats of instructions that were supported or like given to us, right? Which were given to us, and we had to just implement this subset. Now, n power ISA is a very small subset of instructions, actually, just 50 odd instructions which are present there, and just these instructions, right? So nothing was complex for us, just this was entirely provided to us, and we had to just implement it. Right, so whatever you have seen right now is approx 10% of the entire ISA. So let's go and look at the entire ISA if it loads up. Right, so this was the ISA manual that was provided to us by our professor. And yeah, again, it belonged to our course and also to our college. And you see the same information provided here. Right here is something which I've not included in the slides, which is a description of the register files. So what are the exact register files present? We did not look at that because it was beyond the scope of our work. These are the instruction formats which I put up on the slide as well. And just in the ISA itself, you will always see a description of every field, right? So what is PO? It stands for primary opcode. What is XO? It stands for extended opcode. And if you see these fields, right, RS, RA, RB over here, these are nothing but the GPRs or the general purpose registers, which are to be used as either a source or a target, right? So RA can be used as a source or as a target, whereas RB and RS can be used only as a source. RT, wherever you see, is going to be used only as a target. So these are our register indices, I would call them, basically locations in the register file where data is present. So that is what RS, RT, RA, and RB signify. Similarly, you have some other flags. For example, if you see this RC flag here, which is just a one-bit flag, then you have LK, AA. So these also have special meanings. But again, I did not look at them, right? Because that was, again, not needed for us. But yeah, the ISA is a place where the manual is a place where you get all information about the ISA. Similarly, you have other description of all the fields which you would see. You see this SI field here. This stands for the signed integer immediate field, right? And what this means is your instruction is going to contain, let's say, this D instruction. It contains the SI bit field. What this means is whatever integer is present here needs to be sign extended to 64 bits and then used by the ALU. I'm sure you guys know about this also if you have studied basic RISC 5, for example. So that is what this is. That's for the sign extension. Then comes the actual part of the ISA. I mean, just going in more depth about the instructions itself. These are the type of instructions which are present in the ISA, right? You have the add instruction, you have the add immediate instruction. Similarly, you can see you have the and immediate instructions. Moving down, you have your NAND, NOR, or immediate subtraction. So all of these kinds of instructions are present. And what you're also provided in the table is a mapping, right? You're given so you're given a mapping here. So you have a binary instruction fields here. It's going to specify what is the OP or the primary opcode, the XO, which is the extended opcode, and all of these information about this particular instruction are present. So what this means is if you look at the OP is 31 here, and this XO bit is 266, right? This XO field is 266. What this means is for the primary opcode 31 and extended opcode 266, if this is present in any given instruction, then that instruction for sure is an add instruction, right? Now let's look at AND instruction. I told you add and AND are similar, but how? So if you see this 31 here and 31 here, both of them are the OP or the primary opcode, right? And since both of them are 31, you look at the XO or the extended opcode. Right now in the AND case, it is 28, and in the previous case, which is the add case, it is 266, right? So as you can see, a combination of OP and XO bits will tell you what the actual kind of instruction is. And our job is basically that, right? In our programs, you have to identify the kind of instruction that we are looking at. All right, so this is some information about the kinds of instructions which are present. And yeah, and then you have the next. So these were your arithmetic instructions, obviously. Yeah, so these were your arithmetic and logical instructions. Moving on, you have the data transfer kind of instructions, which are your load double word, load word, these instructions, right? Yeah. So your loads and stores are also defined here. Moving on, you would see that you have the shift and rotate instructions also defined here. Finally, you have the control statements, which would be dealing with things like unconditional branches, function calls, functional returns, branch conditional relative, and all of these fields, right? All of these kinds of instructions which are going to be present. So that is what this section is all about, right? And then you come to the end. I mean, no, you don't come to the end. You see some extended mnemonics and some information about the memory layout and the addressing modes. So this is some information which was present, and all we were supposed to do in this instruction was that we had to implement an ISA, which was provided to us via this manual, which could handle all these instructions, right? That was our aim. Now, before I move on any further, let's open up my PPT. Yeah. So before I move on with the processor workflow, I want to show you the IDE which I used to make this project work. So I'll just open up a new window. So the IDE which I've used is an online IDE, which is MakerChip. So let's look at how MakerChip works first so that you even understand my code when you see it. So it shouldn't be completely random. Right, so you just have to go to makerchip.com. If you guys are trying it right now, hands-on, you can do that on your computers. So I'll just tell you a bit about MakerChip. It's nothing, it's just a platform which gives you a place where you can create any digital sequential logic that you want. And all of this is possible within your browser, right? And it has two major breakthroughs in as far as productivity is concerned. One thing is that there is a tight coupling or a tight integration of your design, simulation, and your debug capabilities, right? So when you actually run your simulations on this online tool, your debug statements are very tightly coupled to your code and debugging becomes very easy. The second thing is that you don't actually have to spend your time and energy on getting those output waveforms, on getting those output simulations. All of that is automated. So all you have to do is write a script. That script is going to be in TL Verilog or transactional level Verilog, HDL. And once you write that script, it's just going to compile. Now, this TL Verilog, HDL, people who are not aware of it in the meet, it's very similar to Verilog and System Verilog. And if you guys have had any previous experience with that, catching up with TL Verilog is going to be very simple. However, if you guys know TL Verilog, then obviously it's just bread and butter. You can just start off editing. It's just any other IDE for you, right? So you would click on this launch MakerChip IDE. And what this does is it creates a sandbox, and this sandbox is going to contain one script, right? And this script is what you would edit. Now, there are a lot of background processing which is going to happen on your file, and it's going to generate your system Verilog files and actually produce the simulation outputs. All right, so on this IDE, as you can see here, on the left, you have this editor here, right? And then you have a log section where you'll see the logs of whatever is being executed, right? And then you have an editor. Now, in this editor, you write some TL Verilog code. You can write some system Verilog code, right? You could also write Verilog code here. So anything, right? You will just enter code in this section. What you see on the right-hand side is your simulation or your output, right? What the diagram does is it makes a high-level module design of whatever code you have written, right? So MakerChip tries to understand your code and develops this particular module, right? It produces the high-level module design. Then you have the waveform section. So if I just zoom in, you'll see that there are these clock cycles, right? There's a clock variable. It's a global variable and it's just signifying the clock. And finally, all the variables you have used. For example, right now you will see there is one variable, which is reset. And this one variable has been shown here. So that's the reset variable. And it's set to 1 for one clock cycle. And then it just stays 0, right? That's the point of the reset signal, that it resets your CPU. So that is what this is, right? All the variables that you use will be listed here and it's a waveform. Now, let's move on to some tutorial, right? Let's pick up any tutorial and look at it. So let's look at some combinational logic. Even before that, if you just go to your editor here, and let's say over here, I write any simple expression. So let's just say I write A is equal to anything, let's say B and C, for example, right? So if I write this, what is this expression doing is nothing. It's just using two variables B and C, ANDing them. There's the logical AND operation, and it's going to store the answer in A. Now, if I go ahead and compile and simulate this, you see the diagram, right? It has two variables B and C, right? And you have these data flow arrows, and you can see that A is actually accessing the values B and C, right? So this is what it looks like. This is what this code is doing. And if you look at the waveform, we'll zoom, right? So now you see B and you see C here. Whenever B and C both are 1, only at those positions A is also 1. And yeah, it's a basic B and C. And the values are being stored in A. So what MakerChip has automatically done for us is it has identified all those variables whose definition we have not created, right? Basically, we just used B and C, but we never actually defined values for B and C. And random values have been assigned to B and C, which are 1-bit ones and zeros. They have been randomly assigned. Based on that, A has been calculated and a waveform has been made, right? So all this process is made very simple with TL Verilog. So if you see, look at the tutorial on combinational logic, it's also going to contain the same things, right? It's going to contain all this stuff. Then you can also make a mux. So if I just load the mux example and go back to the diagram, you see how mux is going to work. It's just a ternary operator, right? So muxes are simulated as ternary operators. Very simple. So you can have a chained ternary operator or a single ternary operator, and that's it. So if this variable big or this bit big is set to 1, then the value stored in num1 is going to be 255, otherwise it's going to be 0. And if I go into my waveform, right, so whenever you look at big, whenever the value is 1, you'll see that num1 is also going to store ff, which stands for 255, right? And then whenever big is 0, here in this section, for example, the value is 0, right? That's how it's a normal ternary operator. Similarly, you have the big, medium, and small variables, which are being used in assigning values to num2. So depending on what you store in big, medium, and small, the num2 is going to be assigned whatever value there is going to be. All right. So this is about the combinational logic. Let's go ahead and look at some sequential logic. So for writing a sequential logic in TL Verilog, what we need to understand is how do you write it in Verilog. So what you would do normally in a normal system is you would assign a flip-flop, right? That would store a previous state of a value. And based on that previous state of the value, you can look ahead and update your current value. For example, if I was making a countdown timer, right? Or a basic counter, for example, we just went from 1 to 8 and then reset to 0, again went to 1, went from 1 to 8, reset to 0. If you're making this kind of a setup, then what you would need to be doing is you would define some variable counter, and let's say it's a 4-bit value, okay? And we would assign it to become equal to whatever the counter variable was initially and plus 1, right? Now, how do you specify that this counter variable that you're trying to access here is going to be a previous value? So it's a very simple thing. You just add this extra bit of information. Now what this means is you're going to take the counter variable, whatever value it stored from one cycle ago, right? That is what this is doing. So it's going to create a flip-flop for you internally and store that value for one clock cycle and pass it on to the current clock cycle. That is what is going to happen. Now this program will immediately not run because at clock cycle 0, counter is not going to be defined, so it's going to give you an error. For example, if I just go ahead and compile and sim this, your diagram will appear correctly. Everything is going to look fine, but it's not really going to work. Okay. So what we will be doing is we will be testing if the reset signal is true. If it is true, we are going to assign the counter variable to become 0. Otherwise, what we are going to do is this operation, compile and sim it. Just look at the diagram. What has happened in the diagram? I have a counter state here, right? And it's accessing a flip-flop. Now all these empty boxes are basically, you can treat them as memory devices or registers or just flip-flops, right? It's accessing the value of the flip-flop, which is one clock cycle behind the current one, and using it to update the counter value. That is what is happening. If I went into the waveform also and zoomed in, you can see it's a proper counter, right? It goes from 1, 2, 3, 4, 5, 6. It is going on that way. And each of these operations takes one clock cycle, right? So you can see one complete clock cycle, the value remains 1. Then it becomes 2, then it becomes 3, then 4, and so on. So that is what this piece of code is doing. Now, let's say I tell you to improvise and convert this counter example into a Fibonacci number generator. How would you do it? In Fibonacci generator, what you need is you need to store the values of two states, right? Also, you know that Fibonacci numbers start from 1. Now you need to store two flip-flops, right? Which are going to store your two previous states. So you're going to just make it 2, right? This is going to say, bring me the value of counter, whatever it was, two flip-flops, I mean, two clock cycles ago, right? And when I compile and sim this, look at the diagram, I've introduced another flip-flop here, which is 2 clock cycles behind the main clock cycle, right? And this counter variable is going to use both of these flip-flops to update its current value. And if I look at the waveform, you very well see the pattern, right? You see 1, 2, 3, 5, 8, D. D is 13 in hex. That's what you're seeing here. This is the Fibonacci number generator. What you would normally need to do is create two flip-flops and do that. All of this is being achieved on MakerChip with one line. So it's a way of writing small, concise code, which is just, and you see the waveform generation is so simple that you don't have to actually create a VCD and things and then run the graph. But yeah, I mean, that is what TL Verilog is doing for you. And my project was done on TL Verilog. Now, the reason I did not show this to you before is that my project looks like this. So if you saw this directly, it'd be pretty productive. You wouldn't understand a lot of stuff here. That's why I went ahead and showed you how to work with TL Verilog first. Now, so now what I will am I still audible?
Yes, sir, you are audible, but your voice is a little low.
Oh, okay. Is it still low? Hello?
Yeah, yeah. Sir, we can hear. It's okay. It's okay.
Okay, cool.
You may continue, sir.
Okay, and my screen is visible, right?
Yes, sir. Yes, sir. Your screen is visible.
Okay, brilliant. All right, so yeah, and this project was done in a group of 4. So now what I want you guys to do is, do we need to take a break now? We could take a break where people could explore whatever I just talked about, maybe like in this PPT, whatever we have talked about so far, you could take, I guess, 15 minutes to reflect on this and come back. Is that required, or can we move ahead?
Participants are requested to please put in the Q&A window if you're having any queries, so that by that time Ishan sir may reply to your queries, and you can have some time on the slides, and if you have any queries you can just put in the Q&A. Sir, I guess there are one or two questions are there in the Q&A window.
Okay. Could someone read them out to me? I don't think I can look at them right now.
Yeah, there's a one question. So can we work on VHDL with this maker chip?
Yes, you can actually work with VHDL. Right, so I'll just show it to you. Okay, so what happens here is you see system verilog here, so you can very well start up a system verilog block here and write your system verilog code here. But also what happens is here you can just go and show verilog. So whatever TLV file you're going to write here, the same basically whatever backend they're using is going to convert all of this code into system verilog and provide you with that code. So second, right here you see. So whatever code you wrote is going to be converted into system verilog HTL itself. And if you're comfortable with verilog, yeah, I mean catching up with TLV is actually very simple. In fact, I did not know about this at all, and this entire project took 1 month. And main parts of the project obviously came towards the deadline, so it was pretty much finished in 2-3 days. But yeah, it's very easy to catch up if you know Verilog. It's pretty much the same code. Is there any other question?
Yeah. So the next question is, how much does TL Verilog simplifies design compared to Verilog?
Okay, so I mean that question is a little bit general, but if you have written code in Verilog before, you will very well know that you have to write a test bench on your own, right? So you design the Verilog module on your own, but you also have to write test benches where you actually send data to your module, and then you have to run the same thing in your terminal and produce a VCD file. Now you use that VCD file onto a graph maker or a simulator of that sort, and it's going to generate the graph from the VCD. So you would have gone through all of this process, and yeah, that process is pretty hectic, right? You have to create the VCD file and do all of this stuff. But here with MakerChip, you have to just write this one line of code. And this one line of code, the test benches are automated for you, right? Because you have this counter variable set up on its own. You don't have to do any graphing, plotting, nothing. You just write this one piece of code, compile, and the test benching is automated. So I mean, test benching takes a lot of time, and if that's automated, it's a great thing, right? So that's what is happening. Is there any other question?
Yes, sir. Sir, the next question. Using Verilog, can you please give small example?
Right. You cannot enter direct Verilog code. You could enter system Verilog or TLB, but you can look at the code which is generated, right? And you can see the 3 variables which are being set, A0, A1, and A2 instances of the counter. And that's it, right? And this is your normal Verilog example. In Verilog, you would have an always FF or always flip-flop. And on the positive edge of the clock cycle, you would actually update the value, right? And this is your assign symbol. So this is your code, this much. This is your Verilog code which has been generated. Now, if I was to write the same thing in Verilog here, I would have to write these 5-6 lines of code, but I wouldn't go ahead and do that since I can do this. I mean, I will be coding only in TLV now. In fact, I won't even be coding. This is just for you to get an experience of the IDE. But yeah, if you're just seeing this TL Verilog code, you can go ahead and explore. There are actually a lot of tutorials here. You can see the pipelining tutorial as well. I'll show this to you in some time, but it's crazy, right? You see all of this stuff and learn on your own. It's pretty epic.
So next question is PO the MSB of the instruction?
No, I mean, it starts from the MSB. So if you just look at manual, right, you see these diagrams, right? You see 0 to 5 bits, right? 0 to 5, starting from the MSB, of course, but 5 bits from the MSB is the PO bits, and it's the same everywhere, right? Similarly, EXO bits are going to be from the bit numbers 21 to bit number 30. That's going to be the EXO bit for the X format. Similarly, for XS format, the EXO bit is going to be different. Yeah, PO bit starts from MSB, but it's not just the MSB. Is there any other thing?
Yeah, so does maker chip do synthesis of hardware too?
No, actually, we were looking at this some days ago. It doesn't, I mean, it generates the system Verilog files for you, but it also imports some of its own proprietary packages. For example, if close it, okay, I'll just show it to you here. So basically, when you generate the Verilog file, it's going to create the system Verilog code, right? But it includes some packages of its own. For example, here, this one, and you have the topgen.sv. So all of topgen.sv is here, but okay. I mean, it's going to import some packages. Now, good luck finding these packages. If you find them, of course, you can burn them onto the FPGA board and try running it. But that's about it. I mean, it provides you the code, the system Verilog code, but you just have to find these packages. If you're able to do it, go ahead with it and try to do it. But I've not tried it.
Okay, sir. So next question, is it possible to design for machine algorithms in maker chip?
What algorithms?
Sorry, sir.
What algorithms is it possible to design?
For machine algorithms in maker chip.
Oh, really not aware of this.
Okay,
Sure.
sir. As a next question, what about test bench for VHDL? VHDL, we have to write or generate automatically.
Yeah, you don't actually have to write test benches as I showed you. In VHDL, you know that you have to make test benches and those are not automated. You have to code them up along with your module. But here it's automated, right? So yeah, that's again the same thing. All right, I think we should not take any more questions, otherwise the session time will get reduced. I think I'll just move on. We can take these questions up later. Also, I'll drop my email address at the end. You could just reach me out there as well. Right? Okay.
Yeah.
Let's move on.
So Ishan sir, I guess you are also in the Slack channel.
Yeah.
Yeah. So so like participants, if you have any more queries, so you can put in the Slack channel.
Yeah, that'll be nice too.
Yeah.
Epic. I'll answer them there. Cool. All right then. Let's move on then a little bit more of a tutorial, and then people in the chat, till then you can tell me if you need a 15-minute break to just experiment with MakerChip, and then I could come back. But in the meantime, I'll just cover up one tutorial and then I will just ask for the poll. You see, what are pipelines, right? I just told you what pipelines are. Pipelines are basically ways in which you can overlap two or more instructions so that the CPU utilization increases, right? And that's what a pipeline is going to do for us. So I'll just open up one pipeline example. Right, now in this pipeline, just ignore this for some time. What's happening in the pipeline is you have a stage which you can call 1, you have another stage which you can call 2, and another stage which you can call 3, right? So you give your pipeline stages. So this is the first stage of the pipeline, the second stage and third stage. And in each of these stages, you can perform some operation. Now, if you look at what is the Pythagoras theorem, what we have to initially do is you take in a number A and a number B, and you're supposed to find the length of the side C in the right angle triangle whose sides are ABC, right? Where C is the hypotenuse. So what you have to do is calculate A square and B square. In the next clock cycle, you find C square, which is by adding A square and B square. And finally, you find C in the third clock cycle by finding the square root of the C squared, right? So that is what you want to be doing. Now, why are we using clock cycles for this, right? Why not directly write everything in one? Because this is combinational logic, right? And if you want to make it sequential in some sense, you need to assign them different clock cycles, right? You need to assign them different stages of a pipeline. Now, stages of a pipeline are some things that run in parallel with each other, but they have a sense of sequence in them, right? That's basically the definition of a pipeline. They run parallelly, but the same instruction goes through every stage of the pipeline. Hence, there is a sequence sense also in that. So if I was to just zoom in back, a complex example. Okay, so if you take, I'll just show it to you in the diagram. Compile and sim. So if I compile and sim, yeah, you can see here on the right hand side that you have three stages, right? Stage number 1, stage number 2, and stage number 3. In stage 1, you are accepting inputs A and B, and you're finding their squares, right? Now these squares are stored onto flip-flops, which are going to be accessed in stage 2. And in stage 2, you're going to find C square. Stage 3 is again storing this information in a flip-flop and accessing it and making it the value C. So if you see here, C square is generated in stage 2 and C itself is calculated in stage 3. So if I look at the waveform and zoom in, you would see that the value of C and the value of C square are, how do I say, are one cycle apart. For example, 18A is what? In 18A is 32 plus 8 into 16 plus A, whatever that is. Its square root will come out to be 14 in hex, and they'll be one cycle apart. That is what this is ensuring. A simpler example would just be that of a counter, right? You could write a counter. You could even try doing it yourself now. Make a counter variable here, right? And increment its value in stage 2. You will see that the incrementation happens in, like, it happens one stage back. So if I was to just make a counter variable and set it up to be, so if the reset button is on, I would just set it to be 0. Otherwise, I would take in the previous value of the counter and I would add 1 to it, right? So this is the normal counter code. But what I want to be doing in the stage 2 is generate a new variable. Let's call it variable var, call it var1, and make it equal to counter plus 1. So how would I do that? I would make it equal to counter plus 1. Plus 1 would not be equal to C, we'll make it into 2, right? So now I have a 2-stage pipeline. I'll compile and run this. And yes, so as you can see in the code, I'll just compile and run this. And as you can see in the diagram, what has happened is I have 2 states now. Basically the pipeline is called calc. This is the name of the pipeline. So if I was making a CPU, I would name this CPU. It's basically a namespace, right? You can name it anything. In my project, I actually used CPU as the name of the pipeline. But you can name the pipeline anything, and it's going to have stages. Now, stages are represented by the number. So there's a first stage and there's a second stage. The first stage is using the variable counter, right? And the second stage is using the variable var1. I should probably make this a 4-bit value. Otherwise, this also a 4-bit value. Right. Now the diagram will obviously look the same since I've just changed the dimensions. Now, if you look at the waveform, and if I zoom in, there you see, do you see some pattern, right? Do you see some pattern? What's the pattern? Now, if you look at 1 clock cycle, the counter variable is getting incremented every time, right? It's going from 1, 2, 3, 4, 5, 6, and so on. But if you see the variable 1 counter, which is supposed to hold counter into 2, is actually 1 clock cycle behind, right? So 1 was set here, counter became 1 here, but variable 1 became 2 only 1 clock cycle later, right? So if you see, counter and variable 1 are simply 1 clock cycle away from each other. They're working at a difference of 1 clock cycle. And that is what the pipelining is doing. It has a sense of sequence in it, right? So you can see that variable 1 is always 1 cycle behind the counter. But again, it's combinational logic within the stages themselves, right? So that is the concept of pipelining. This is something I had to cover. Now in the chat, if some people have told if they need a break or not. Was the result there?
So the participants put their questions in the Q&A window, and so they are finding it difficult to get your voice. They are finding your voice to be too low.
Is it very low? Like, am I?
Yes, sir. Yes, sir. It's quite low.
Okay, let me just check that.
And participants also, I would request you if you can please make your system volume to be 100%. Then also it will resolve this.
Is it any better now? Is it any better now? No.
No, sir. No, sir. It's still low.
Okay. Can I get
Yeah,
5 minutes?
yeah. It's better now, sir.
It's better now?
Yeah. Yes, sir.
Wonderful. Actually changed nothing. Okay. If it's better now, then cool. All right. So do people need a break? Is that also a thing in the chat? Like we could take a break.
So yeah, participants, please write in the Q&A window if you need a break now or sir can continue.
The break will obviously be for experimenting with MakerChip, so it's not like a snacking break or something. You can just take a look at MakerChip if you want to explore something.
So the participants are asking to continue.
All right, let's continue then. So you have looked at what MakerChip is, and let's move ahead with our presentation itself. What I'll be doing now is I'll be using so what I'll be doing now is closing this MakerChip sandbox. This was for editing only. And this is the actual thing that I've come to present here. This was the work I did as the assignment. And I'll quickly just move this to the left and zoom in. Right. So you see here, my purpose was to make a 5-stage pipeline, right? I'm sure you guys would have tried making a pipeline in Verilog. But what happens here is it's very simple, right? As you saw that creating a pipeline of 2 stages was already very simple. This is a 5-stage, just a little bit more complex pipeline. You have a stage 0 here, which is just for setting up variables. This is a stage 1. Then there is a stage 2 at the top. There's a stage 3 here. Moving to the bottom, there's a stage 4. And finally, you have a stage 5. Along with this, you see here, there is a register file. So this register file is a device. And whichever pipeline stages are going to access this register file, for example, register file is being accessed in stage 3, 4, and 5. Similarly, you have the D memory, data memory, which is going to be accessed in 4 and 5. In 5, it's not really being accessed. It's just being stored in a flip-flop. So yeah, that's the thing. And then you have the instruction memory, which is just going to be accessed in the first stage, which is your instruction fetch stage. I'll be covering this up in the PPT as well, but okay, you see that this is a 5-stage pipeline indeed, and this is what I had designed, right? You see a lot of boxes here, and looks fairly complex, but we'll break this down. We'll try to break this down as much as possible. All right, so start off with the PPT then. All right, now we'll be looking at the processor workflow. So how did we go about actually making the project? The ALU is a very simple device, right? It just takes in two values A and B. In our case, these two values are going to be 64 bits each, right? So I'm going to take in two 64-bit values into the ALU, perform whatever operation is needed, and then the output is also going to be a 64-bit output, right? So that is what our ALU is going to do. And these were the four classes of instructions, as I told you, which we handled in the assignment. One was arithmetic and logical operations. That could be your addition, subtraction, and their immediate equivalents. And by immediate equivalence, I mean that if you have addition, then you also have the add I instruction, which you have to take care of. Similarly, if you have the sub, then you have to take care of sub I also. So these arithmetic operations are being taken care of. Then you have the logical operations, so AND or NAND, and also their immediate equivalence. That's also going to be taken care of. And moving on, you have this, which are memory operations like loads and stores. And yeah. And finally, you have a comparison statement, which is going to be used for branch evaluation. So your ALU has to take care of all of this stuff, right? This, I mean, normally you would have studied this when you were studying Verilog as well. But yeah, that is the concept being used here. Then this is a sample 5-stage superscalar pipeline. Why have I written superscalar here? Because if you look at the ALU here, the ALU itself is divided into 5 parts, right? You see something like an ALU I here, which is going to handle instruction related to integer kind of data. Then you have M, then you have FPU, which stands for floating point units, right? So for different kinds of input data, different parts of the ALU can be called, and the superscalar pipeline will allow you to make the pipeline more parallel. For example, as you know, like if you have two instructions which are trying to add two numbers, they cannot run parallelly because the ALU can only add two numbers for one instruction at a time, not for two instructions, right? But if one of those numbers was integers and if the second instruction was dealing with floating point numbers, now what happens is that your CPU itself or your ALU, the processor, can actually take up both those instructions at the same time. Like both of them are performing the add operation, but they would actually hit different units, right? And that makes it superscalar. Like that is what it means. But what we implemented was just the I set, because our ISA did not support M and floating point units to begin with. So we didn't have a superscalar pipeline. We just had a normal one. But more importantly, what you need to see in the CPU namespace is that there are 5 stages. The first stage is the instruction fetch or the IF stage. Second is the ID or the instruction decode stage. Then you have the EX or the execution stage, the MEM or the memory handling stage, and the write back stage. Now, pretty sure you guys also know about what the significance of each of these parts are. The first one, instruction fetch stage, is going to access your data memory and fetch an instruction, right? That's it. Instruction decode stage is going to access the parts of those instructions and determine what exact kind of an instruction it is. Based on that, your control unit values are going to be set. So that is what the instruction decode stage is going to do. Apart from this, the instruction decode stage also has access to the register files. So any data which is needed from the register files is also fetched in the ID or the instruction decode stage. Moving on, you have the actual execution stage where your data elements reach the ALU, execution is done, and a final output is obtained here. Now, based on what this output is, and depending on the control signals that you have generated in the MEM stage, you would be accessing your memory device, right, which would be your RAM. You would be accessing that device in order to perform load or store. Finally, you have a write back stage where you're going to write back instructions to the so you're going to write back instructions to your register file. So if you see this write back arrow, it's going to go and it goes into the register file. That's it. So that is what the write back stage does, right? So these are your 5 normal pipeline things. Let's move on to the next slide where I've described this in a bit more detail. The IF stage is used for PC evaluation and for instruction fetching. ID stage for instruction decode and register data reads. EX is for execution and also for effective address calculation for the MEM stage. Finally, you have the MEM or the memory access stage and the write back stage, right? Now coming to our problem statement. So we knew in theory how to make a pipeline, as you guys already know. And my task was to use TL Verilog and extend whatever we had studied for RISC-V architecture, extend it and build it for a subset of the power instruction set, right? And that subset was called the N-power ISA instructions, right? So these were the set of instructions. We were given a manual as I showed it to you already, right? Given this manual and this problem statement, you have to come up with a meaningful program that uses the N-power ISA and runs, basically, right? You can come up with any program and it should run. So sir gave us a lot of options about what kind of program should run on your pipeline. For example, a simple program like adding the elements of two arrays should work on your pipeline, right? Simple loops should run on your pipeline. So you could take up any one such example and make it run on your pipeline. So that was the assignment. So moving on to the actual project. How was it done? It was done using MakerChip, and a link to the GitHub repository is also here, right? Now, after this session is over on the Slack channel, I think I will just drop my PPT so you guys can actually access this GitHub repository. But for the meantime, I'll just show you the repo. Yeah, this is the repo, nothing crazy, but what it contains is the link to my MakerChip sandbox, and you can look it up here. It's in the README. Yeah, so that's in the README, and that's it. So I'll just start off directly without any more time usage. Okay, now moving back to this screen here. All right. So these are some libraries which I needed to import. Now what these libraries do is that they are already setting up a register file for me and an instruction memory and a data memory for me. So these three devices are being set up for me already. What I need to do is I need to override some of the parts of this existing package and make them work for me. Finally, I need to design the whole processor. Right, so how you look at any code which is in MakerChip is in two parts. The first part is that MakerChip provides you with the devices you need. What are the devices? The devices could be register files, they could be your entire memory hierarchy. All these things are already provided to you as devices. What you have to do as a programmer in this one script file that you have, in this script file, you have to make the connections. You have to join these devices, right? And you have to write the code for that. So you have to basically design your control unit. You have to design your ALU and see how they're going to interact with each other. That is your primary purpose in life. So entire data path has to be designed by you. The data elements are being handled by MakerChip. So let's move on to the overloading, which I've done, right? Library code just starts here. First of all, I wrote this instruction. Any one of you, whoever wants, can see and tell me what this program is doing. Just look at this code and try to figure out what it's doing. Initially, there's a register X14, which I'm setting to 0. Then I have a register X12, which I'm setting to 10. I have a register X13, which I'm setting to 0, right? Let's say X15 is a register that stores some input value. Let's say it's 20 for now. Okay. So let's say the X15 register stores the value 20. Now to X14, I'm adding the value 20 every time. I said every time because there's a loop here, but fine. So in X14, I'm adding the value which is stored in X15, and then I'm incrementing X13. Finally, I'm checking if X13 is lesser than X12, which was 10, and I'm looping if it is lesser than that. In between, you see a random store and load instruction. So if you just look at it very carefully, let's not go with the trouble of reading chat again and again. You'll see that this code is basically a loop, right? It's a simple loop. And what this loop does is it evaluates the value in X14. What it's doing, it's adding X15 again and again to it. Now adding again and again is multiplication. Hence my code is producing the multiplication tables for whatever number is stored in X15, right? That is what my program is doing. Now, what am I simulating then? simulation requires a start condition, it requires an end condition also, right? It needs a pass or fail condition. So what I thought I will do with my program is when my system is running and doing multiples of a number n, I'm going to check if a number x is actually present in the multiplication tables of the number n. If it is present, my simulation passes. If it's not, it fails. So for example, I provided the input here as 20, right? And finally, at the bottom, you will see in the past condition, I'm checking for 100, right? So in this case, my simulation, if you just go to the logs, it would say passed. But if I was to change this number to anything, let's say 21, for example, right? And I will run the simulation again. If you go back to the logs, it's going to simulate everything. And the simulation is going to reach max cycles, which is just another way of failing. Now, when does the simulation fail? The simulation fails when you actually hit a fail condition or when your simulation times out, right? These are the two ways a simulation can fail. And that's what has happened. This is one of the ways. So that is what is happening, right? So if you enter 100, it passes, otherwise it doesn't pass. Why? Because 100 is present in the multiplication tables of the number 20. That's what my code is doing. I mean, the code is working. That's why I'm being called to present this. But yeah, you got the point. Let's look at what is actually happening. So what I've done is this is the instruction memory block. Is my text visible on the screen? Should I zoom in or is it fine? Are the characters visible?
Yes, sir, it's visible, but it would be better if we can like zoom a little.
Okay. Yeah, this is better.
Yeah, yes, sir, it's better now.
Brilliant. All right. So you see IMEM here. IMEM stands for instruction memory, right? What I've done here is all the Verilog folks here, Verilog code. What I've done is I've assigned the variable instructions to hold an array of instructions. That's it, right? This is an array of instructions. Now, how did I get these instructions? These instructions are coming from here. You see these instructions, right? These are very RISC-V kind of instructions because add I, BLT, LDW. These are words that RISC-V or RV64I uses for its instructions, and that's what has been used here. And I have just encoded these in the power ISA format, which was given in the manual, right? So that's what I've done. I've encoded these instructions in that format and stored it. Now, what my program should be able to do is, given this set of instructions in the instruction file, in the instruction memory, it has to be able to decode these instructions and perform the operation, right? And my program should run. Basically, I should be able to simulate whatever I want using these instructions. So I have these instructions here, and these instructions have been encoded and checked many times. So they are correct according to the manual. If someone wants to take it up as an exercise, you can take a screenshot of this here and check if this actually maps to this. Later on, when I share the PPT, you can check it up. So whoever is interested has already taken a screenshot now, I believe. Moving further, we'll come to what this section is doing. Not yet, we'll look at it a bit later. So I have overridden some functions of IMEM or instruction memory. Basically, I've fed in my instructions. Now, what I need to do next is look at the register file, right? And I need to overwrite some conditions in the register file. So what happens during a write and what happens during a read is something I have to define on my own. What happens during a write? If the write enable signal is set, that bit is set, then all I need to do is I need to put in the write data. Otherwise, I need to retain whatever value was already present, right? I need to retain it. So that is what this thing is doing. So it's going to set the register value at whatever location I have specified. If the CPU has a reset signal bit set, then I set all my variables to 20. Why 20? Because in MakerChip, there is no way you can take an input from the user, right? So your input has to be fed in via this script itself. And this is my input. Basically, when the CPU resets itself, I set all the registers to the value 20, right? And what this does is it's going to act as an input for me, and that's what is going to happen. Finally, if the write signal is true or enabled, then I set the a register file write data value has been assigned to the register file at whatever location was specified. Otherwise, I just retain the value. This is some code which I've taken from the library itself. Now, where is the library? The library is at the link which is provided here, right? So this link over here contains that library. You can take a look at it later. But this is just coming from the library. I've just overridden a set of instructions for the write. Similarly, for read also, it's the same thing. Read enable 1 is going to tell if basically this register, no, it has 2 read ports obviously and 1 write port, as a normal register would have in your RISC 5 course also. So that's what it contains. There are 2 read ports and 1 write port. The write port has been configured. Now for the read port, I check if the enable signal is true, I enter this block. If the enable signal for port 2 is on, I enter this block, right? And what do? Nothing. So if the enable signal is true, this data 1 is just going to be set to that particular value, right? And that's it. And remaining is just library code. So this is coming straight from the library. All I have to worry about is this value variable. So that has happened. And this is how read has been configured. That's how the register file has been overridden. Going back to the PPT, if you look at it, what were the key components discussed so far? First is the instruction memory setup. So I've written the assembly code for the program I want to simulate. I encoded all these individual instructions according to the n power ISA given to me. I encoded all those instructions into that binary form. And then I fed all those encoded instructions into the memory, right? Now later what I'll be doing is in the IF stage of the pipeline, which is the instruction fetch stage of the pipeline, I'll be invoking this memory. I'll be pulling out instructions, whatever I fed in just now, I'll be pulling them out one by one, right? And the kind of abstraction that MakerChip provides to the IMEM data memory is that it treats it as an array, right? So if you do instructions of 0, it's going to get the 0th instruction. Instruction of 1 is going to get the first instruction. That's what is going to happen. And it's going to be treated as if it is an array, right? That's the abstraction that the instruction memory is going to use. All right, so again, there's just a screenshot of that code which I showed you just now. Next, how do I set up the register file? Okay, that also I just explained to you already, the read and write stages. So I set up the register module for reads and writes, overriding the defaults pertaining to our use case, right? I've done this. Now on line 66, which is here, you can see line 66 contains the value 20, which is like an input to our program. So there is a mem set for the entire register when the CPU hits the reset state. And when that happens, I'm going to set it up as an bogus use keyword is something which you'll cover later, but you can read it up here. Bogus use keyword is used to tell MakerChip that these quantities, whatever are specified here, basically data 1 and data 2, are not going to be present in the output graph. So when I plot the waveform, these values are not going to appear in the waveform. Yeah, because they're pretty useless. We don't need them in the output waveform. We need only useful values which are going to be printed. So that's about it. So this is how the register file has been set up. Now let's move on to the actual pipeline, right? Pipeline on the stage 0 is just going to, okay, so let's see what's happening here, right? What is this, guys? This is the namespace, as I told you. The namespace could be called anything. In our tutorial example, I called it CALC, where we found the counter and the Fibonacci numbers and things. Right now, I'm calling it CPU. Now CPU has a stage 0, which is just for setting up. So I set up the reset signal here. I set up the start variable and I set up the initial PC, and also just an increment has also been implemented here itself because the ternary operator already exists. So that's what I'm doing. I'm just incrementing PC here. So PC implementation has happened in the setup phase itself. Now you'll see there is one stage 1, stage 2, stage 3, stage 4, and stage 5. Right. So you see, these are my 5 stages of the pipeline. I'll be opening them up one by one and explaining it to you. Let's go with stage 1. So stage 1 deals with instruction fetch and PC increment only, right? Because this is the IF stage. What I do is I find out the new PC value by adding 4. Why 4? Because 4 bytes. And why 4 bytes? Because every instruction is 4 bytes long. So that's what the increment PC is doing. All right. Next, I have to do IF meaning instruction fetch. And to fetch data, I need to set the read enabled signal to be just the opposite of reset, because if the reset signal is on, only in those cases IF unit has to not work. But if the reset signal is 0, then I can just use the IF memory anytime, or the instruction memory anytime to fetch instructions. So I do that. I specify the read address to be PC, right? So from the PC itself, I get the read address for my use case. Finally, I pull out the instruction, right? I pulled out the instruction variable. Now, as I told you, so right now I have my instruction, right? I have the set of instructions which I have here. And what I need to extract out of these instructions, every instruction contains PO, which is the primary opcode, the XO, which is the extended opcode, and other useful fields like the register files which have to be used. The register source 1 and 2 are going to be present, right? Finally, the register destination is going to be present, right? All of these are present at specific locations within the instructions. So that have been pulled out. Finally, you have the XO bits and the PO bits being pulled out here. Everything is coming from the instruction itself. All right. Some instructions also contain an immediate value, as you would know. And depending on what the PO value is, the immediate values are going to be present at specific locations in the instructions. So that has been configured to use the PO bits, and using a nested ternary, we have done that. Otherwise, I just set it to a 64-bit 0, right? A 64-bit 0 is what it has been set to. So that's how I set my immediate variable. So right now in the instruction fetch stage, I have broken down the instruction into the bit fields. Now what do I need to do next is to decode this instruction and see what this means. Right now it's a set of garbage values. Later I have to see what this actually means. So moving back to the presentation, the instruction fetch stage, in general, we first need to break down the instruction into its component bit fields, right? The order, in order to do this, we look at the XO, PO, immediate, RA, RB, and RS bits, which are present in the instruction as shown in the ISA manual. So where is the manual? Right here, right? You see the PO, RS, RA, RB, XO bits. These have to be extracted. And that is what has been done. Second. Yeah, that's what has been done. So I've pulled out those individual fields. Then these components will decide the operation and the data sources to be employed in the further stages of the execution, right? So these things which I pulled out, the XO bits and the PO bits, these together, these two fields will decide what the exact kind of instruction is, and the immediate RS1, RS2, and the RD fields are going to define the register files and the actual data which is going to be used by the ALU, right? So that's what is going to happen. We'll take a look at it now. So let's see the instruction decode stage. All right. So this is the instruction decode stage, guys. Here we actually decode what the PO bits and XO bits are trying to tell. So if it's a subtraction instruction, then the PO bits and the XO bits are going to be present in this configuration. If it's an AND, add, NAND, NOR instruction or whatever, if it's a branching statement, if it's a load or a store. So all of these are going to be defined by whatever PO and XO bits, right? So that's going to be defined. Now you see a lot of instructions have their PO or the primary opcode bits all as 31, right? In that case, the XO bit is going to be the differentiating factor. So using the XO and the PO bits, I've been able to decide what exact kind of instruction this is. Now, based on this, I would be setting my control signals, right? Next, moving on. Also in the ID stage, we have to also do register file data access, right? So whatever data is needed from the register has to be pulled out right now. So we go ahead and implement that also. I set the read enable 1 and read enable 2 of the register file to be 1, right? And I have already gotten access to RS1 and RS2, which is the register source 1 and register source 2 from the previous stage. I already have access to those variables. And I just set index 1 and index 2 to those two values, right? And finally, I will have access to register file values present at these two indices. Okay. So now I've set Right. Now, depending on the instruction which I have and whatever data I get from the register file, I'm going to set three values, which are source 1, source 3, and source 2, basically three source values. And these source values are going to be used by the ALU in order to compute some stuff, right? What is it going to compute? It's going to compute a result, and that result is going to be forwarded onto the MEM stage after the EX stage. So these are going to be used in the future uh, pipeline stage, which is the EX stage, right? So I find the source 1 and source 2 values, and finally a source 3 value also. You will come to what the source 3 value is, but source 1 and source 2 are going to be used by the ALU as inputs. All right. Yeah. Also, later on, if the ALU decides that this is going to be a branch instruction, not the ALU. If the CU decides if it's going to be a branch instruction, in that case, I just calculate a target branch PC also here. So I just add the immediate field to the current PC. Because if a branch had to occur, then the new instruction to be fetched is going to be this, right? So that is what I've calculated here. Now, let's go back to the PPT and revise whatever we saw now. This was instruction fetch. We already saw this. Instruction decode stage. So this is the instruction decode and the register file reading stage. So we use the components of the bit fields to identify the exact kind of instruction which is present. So this is where I've done that. I've identified the exact kind of instruction. Then all of this information is going to be useful only in the EX stage of the pipeline that we know already. Then we read the register file to get and compute these values as well in this stage. Okay, so we fetch the register file values here and we set our source 1 and source, basically these source values which are going to be used by the ALU later on. Finally, we set the new target PC assuming no branch occurs later, right? So this is our next PC which is going to happen, and that's going to be our target branch PC. Moving on to the execution stage. So are there any doubts in the chat so far? Take them up now.
Yes, sir. There are certain questions are there.
Yeah.
So the first question is in SV, does it take the operations default on clock?
Yeah, correct. So I mean, if you're talking about the maker chip simulation, then in that case, yeah, it's always going to check at the positive edge of the clock cycle. Yeah.
Okay. So next question is, can we synthesis in maker chip?
Yeah, the answer to this question is yes. You could go ahead because MakerChip gives you the SV files, but good luck finding those packages because those are proprietary packages of MakerChip. If you're able to find those packages, yes, you can go ahead and simulate, burn it onto FPGA board and see if it works, but I haven't tried that.
Okay. So the next question is it possible to save the design done on cloud the way EDA playground facilitates?
Yeah, you can actually do it. I mean, they provide only an online sandbox, so it's not possible for you to run the sandbox on your local system. But yeah, you can clone the setting, you can clone the thing here, and you can also save it. How do you save it? I think in project, not under project. Okay, I mean, there is a way to do this. I will just show it to you here. Makerchip.com. Develop in your browser, easy pipelining. There is a way to run it from your system. So all the files are going to be stored on your system. But again, MakerChip is not going to give you access to those packages, which we looked at. So those packages are something you will never get access to. But this code and all of this stuff that you write and the diagrams that you generate, obviously, all of this can be exported onto your local systems, if that was a doubt. Yes.
Okay. So next question is, does it support unsigned numbers for multiplication?
Yeah. Unsigned numbers for multiplication. I think I have not tried that. It just depends on the kind of instruction. So, I mean, this is just normal Verilog code, and definitely there is an unsigned data type here, which you can use. So it should support, but again, as I told you, I've only worked with the I instruction set and not actually seen multiplication or floating point units. So for integers, again, I never thought about unsigned integers. And if they're signed, they are in 2's complement. Yeah.
Okay. Sir, then how to write a combinational logic in maker chip?
So everything you see within this stage, right? Now, so for example, in stage 3, which I will be showing you, so I should probably not show here. Yeah. In stage 2, whatever you see here, no, this is combinational logic. This is not sequential in any way. So whatever is present inside this block is all of this is combinational code. The way it becomes sequential is whatever is present inside this at2 and whatever is present inside this at1. That's in a sense sequential. But whatever is present within a particular stage is all going to be combinational logic. It's not sequential at all.
So there are no more questions.
Okay, so there are no specific questions to this project. Okay, that's fine. All right, let's move on. Guys, if you have any doubts, you can just put it up really in the chat. It could be anything silly or stupid also. And that's because I'm just a third year student. Nothing crazy going on here. Just a normal project. All right, let's move on to the execution stage. Now, what happens in the EX stage, right? Your ALU is going to get 2 inputs and it has to produce an output, right? And our inputs are stored in SRC value 1 and SRC value 2. These are our 2 inputs. If you go back to the PPT, I go a little back to this slide. Here you see there's an input A and there's an input B. You perform whatever is needed and that's the output you get, right? That is exactly what is going to happen here. I calculate the result based on the kind of instruction, whether the instruction is a subtraction instruction, whether it is an AND instruction, if it's an addition instruction, whatever be the kind of instruction, based on that, I calculate the result, right? And it's a nested ternary, as you can see here. It's a nested ternary. Finally, I just set the result as 0 if it's none of these kind of instructions, because that case would first of all never occur. But if it did occur, you should probably end the simulation here. But I've of course not done that because I know my instruction set, because I have only fed it, it's never going to fail. So that case is something I did not check. And depending on the kind of instruction, I just set the result value. All right. Moving on, not moving on, moving up. Yeah. Now this variable here, taken branch, is going to see if the particular value is a branch instruction. And if it is a branch instruction, then I use the SRC3 value. So as we saw here, we are fetching 3 values here. SRC1 and SRC2 are going to be used in the result calculation, but SRC3 value is going to be used to check if it's a branch instruction or not. Again, this is coming from the ISA manual, and I don't know why it's happening. The thing is, whatever is coming from the manual has to be implemented as it is because it's a manual for that purpose. And if it's a branch instruction, this is an extra step that has to be checked. Otherwise, I just set the value to be equal to 0. All right, so that's the taken branch. If a branch has to be taken or not is what is going to be specified by this instruction. Finally, I have this one line of code, which took me a long time to figure out, but again, got it. What this means is basically in your processing, what can happen is there can be a lot of branching taking place. But also because of all this branching and all the loads which are going to happen, there could be a lot of stalls, right? What I mean by stalls are the instructions would have to wait for each other. So one instruction could have to wait for another instruction to get over. And that is what this is, right? So that is what this whole valid bit is going to be telling us. It's going to check from 2 clock cycles before. It's going to check if a valid branch is currently being taken. In that case, I will have to wait this instruction out because this instruction actually need not be executed and a branch has actually already occurred in one of the previous instructions. So that is what is being checked. Otherwise, if a valid load instruction is being executed right now, then also I need to wait. Why? Why do I need to wait for 2 clock cycles for that? I need to wait because whatever output is going to be produced by this EX stage might need the values which are being loaded by that instruction, right? So I wait this instruction out. So what you see is a very bad way of handling a structural or a data hazard. What I'm doing is I'm just stalling the entire pipeline for that much amount of time till that load or store actually finishes, right? So I'm just stalling the pipeline. This is not what you would see normally, like in a proper code. But since this was a learning project, sir just told us that you need not worry about stalls right now, and you can stall the entire pipeline. And that is what we did. I mean, you could come up with multiple solutions to handle stalling, which could be unfolding of your loops, or you could go ahead with out of order executions, right? As you would study in your HPC course. But all of this stuff is there. Right now, I've just stalled the pipeline. Moving on, I calculate the result. I've already explained this part of code to you. And then I check if I'm actually undergoing a valid load instruction, and that is being checked using these 2 bits. Why these bits are working, I'll not go into detail now because that would take a lot of time. Quickly wrap this up also. Then I have a register file write, considering these 3 cases. These 3 cases are just going to tell when my write enable has to be set for the register file, what is the index to which the data has to be written, and the actual data that has to be written is also going to be stored here, right? So if the instruction is a valid load instruction, then I need to take that loaded data and put it in the register file. Otherwise, it's the result which I've obtained from the ALU that has to be stored, right? That is happening here. And the index is also coming. If it's a valid load, then I have to take the destination register from 2 clock cycles ago. Otherwise, I have to take the current register cycle itself, current register RD value itself. RD is basically the register destination index. So I have to store that value. Either I take the current one or I take the one which was 2 clock cycles ago. Is being decided whether it was a proper load instruction or not. All right. So this is the EX stage. And if I go back to the PPT, this is the execution stage. As you can see here, this stage is the compute heavy stage, obviously. We use all the information available from the previous cycles to evaluate the instructions correctly and forward the obtained value to the further stages. What are the further stages going to do? They're going to be the MEM stage and the write back stage, right? They're going to deal with the output of the CXC stage. Finally, this stage prepares the data for further processing or storage, as the case may be. All right, so this is the EXE stage. Moving on to data memory reads and writes. So that's the 4th stage. This is going to handle the MEM stage, where I'm going to set the read and write enabled control signals for the control unit to indicate if it's a valid store or a load location, a store or a load instruction. So for that purpose, I have used the read and write enabled. Finally, I have this DMEM address, which is going to be the address to which I want to write my memory. By default, I've used the address 0 here for reading and writing, irrespective of what's coming from the input. I'll tell you the reason for it. The reason is that I did not have enough time to experiment with DMemory while making this project. Of course, I can look at it now and I will. But right now, it's just going to read and write to the memory location 0. In our case, because then my waveform becomes easier to explain to you. And then I have the write data, basically the data that has to be written. I just store it in the source to value. Okay, that's coming from the ALU again. And in my 5th stage over here, what I have to do is whatever data I've gotten from the memory stage, or the data which is coming from the CPU, either of these has to go into the register file, right? Something has to happen here. Now what's going to happen? The load data is assigned to the memory RD data. And finally, I put in the pass and fail conditions. What is my pass condition? I check if the current value, which is in the register file at location 14, if the value at that location is actually equal to 100 after this load and store instruction, then I can break my signal out, right? So you can change 100 to any number you want to check in the multiplication tables for the number which is on the top when we initialize the registers. So this is what that 100 is doing. It's going to check if the register file at the location 14 contains the value 100. If it is, I tell that the simulation has passed. Otherwise, I consider it to be a failed simulation and it keeps continuing, right? And this is the entire code here. If I just expand this again, and let's see it stage by stage this time, okay? So stage 0, in stage 0, I'm dealing with reset. I'm dealing with the PC variable and I set restart. Now what happens is stage 0 is just a setup phase, so we won't be looking at it in detail. But look at the stage 1. In stage 1, I have IMEM read enabled, IMEM read address, and the incremented PC value coming here. Now based on from where and what I read from the iMemory, I'm going to get some IMEM read data, which is going to finally give me the instruction, right? So at this point, I have read the instruction memory, and you see this instruction here. Now from the instruction, I can pull out a lot of useful information. One is the PO bits, then the XO bits. Finally, I get the register source 1 and register source 2 instructions coming in from the instruction only again. Then I can actually extract the immediate field and the register destination also, right? So I get all these useful bits of information coming from the instruction itself. Finally, all these information, I will just highlight them so you can see where they are used in the future. So if you see, all of this information is going and getting stored onto a lot of flops. And these, so whatever I found just now, right? I found the XO bits, the PO bits, and a lot of register file locations. These are going to actually decide what kind of instruction it is that I'm looking at. So is it a OR I instruction, right? Is it a B instruction? Is it a AND I instruction? So what is the kind of instruction that I'm working with is going to be decided based on which data? Based on the XO and the PO bits, right? So if you see XO and the PO bit arrows all go into these variables, which tell you what kind of an instruction it is. Finally, I have this register file 1 and register file 2 values, which are going to be used later to access, right? This is the register file read index 1 and read index 2, right? This is what is going to be accessed. And from here, we are going to access the register file. You see 2 arrows are coming here, right? From where are they coming? If I go down along this arrow, they're coming from the register file, right? So these 2 data values are coming from the register file and getting stored onto these 2. So register file read data 1 and data 2. These are going to be stored, and as you can see, these yellow arrows are where the data is going to go in this diagram. So they're going to go to source value 1, source value 2, and source value 3. These are what are going to be fed. Now, if you see these arrows which are related to source 1 and source 2, they go and determine what the result is. So if you see the source 2 value, if I just follow the arrow, it reaches result. Similarly, source 1 value also through a flop, it's reaching the result, right? So result is going to be calculated from source 2 and source 1 and source 2 values, okay? That's how the result is coming. Similarly, I check if a branch needs to be taken or not, and that's also being decided. Finally, after all of this hard work has been done, after all of this hard work has been done within the same stage 3 itself, like right now we're looking at the EX stage, right? Within the same stage 3, I'm going to check if it's a valid load instruction, and if it is, then I set my write enabled and the write index for the MEM stage that has been set here. So basically what my EX stage is doing the execution. It's also doing effective address calculation, right? That's what we have studied in the pipeline lectures. And that is what is happening here, fine. Now moving on, these values are going to be used by our stage 4, which is the MEM stage. What's happening in stage 4? You see 4 boxes within stage 4, which are storing the write data and the write enabled control signals. Then the DMEM address, which is basically where the data memory has to be written, and the read enabled, right? So that's going to happen. Finally, have the read enabled data, and all of this goes into the stage 5 where a write back is going to happen. So whatever the load data is, or whatever is the output of the ALU, depending on what has to be fed into the register file, that's going to happen. Okay, so this was the CPU point of view. Now let's look at the device's point of view. So if you see here, this is the register file. It's going to be accessed in stage 3. Why? Because this was the IF stage where you're going to have a write value and the value. Right, so that's going to happen here. It's going to be accessed in stage 3, 4, and 5. Moving to the bottom, you have the D memory, which is the data memory, and that's going to be accessed here in these clock cycles. So basically clock cycle 4, clock cycle 5 is just a flop value, so we don't consider that. In clock cycle 4, and moving to the very bottom here, IMEM. IMEM is going to be accessed in the first stage of the pipeline for reading the instruction. All right, that is what this is. And what I show you next is a waveform that's generated. Okay. So in the waveform, right now live, I don't think I can show you a lot, but what I can show you is how the pipeline is actually working. So there are a lot of values here you see. Yeah, okay, there's a JavaScript heavy thing. So if your PC is actually not strong enough, it's going to take a lot of time to even scroll up and down because there's a lot of outputs. But you see there is this variable result here, right? This is the ALU output. And moving down, I'll just expand data memory 0. That is where I've written all my instructions. So expanding this, it's taking time. Taking time because the JavaScript heavy thing. All right. So we have seen this now. This is the result. And if you see, this is the value, which is present in DMEM. I'll just zoom in. So there's lesser amount of information on the screen. All this crunching will not take time. Okay. So now lesser amount of information on screen. So scrolling is also pretty fast. Okay, now look at this. You see, so one clock cycle ahead. Right. Now you see the values which are being stored into the D memory. The value 28 has been written here. You see the write enabled signal here for the D memory. It was enabled for this one clock cycle. This one clock cycle at the top that you can see. It's enabled for this much time, and then later it becomes enabled here when the data is again changed, right? So that is what the D memory control signal is, the write enabled signal for the memory. Now, just look at it. Look at the result which is being generated. When did it become 28? It became 28 one clock cycle before, right? The data was generated one clock cycle before. And one entire clock cycle later, the memory was written, right? Why did this difference happen? Because data memory is being accessed in stage 4, whereas the result is being generated in stage 3, right? And as we know from the entire pipeline diagram, stage 4 was the MEM stage and stage 3 was the EX stage. And that order of execution has been maintained, right? So that's a concept of pipeline. Whatever has been generated here is being stored over here. Similarly, if you see this 3C here, which has been stored, 3C is a hex value, which stands for 4860. It stands for 60. So that's what this is. And its value was also generated one clock cycle before. So if you see 3C was generated here, right here. So that's just one clock cycle before. So that's what is being stored here. And as you can see, the data memory is storing what? It's storing multiples of 20. So initially it was 0, then it has become 28, which is what? 32, 40. There's 40, then this is 60. If I move ahead, then you see 50 here, which is standing for 80. So these multiples of 20 are being stored and loaded from the memory again and again. And my pass or fail condition later over here at the bottom is going to check against that particular value which I'm getting, right? It is going to be loaded into the register file number 14. Why? Because that is what my load word instruction is doing. On register 14, it's going to load the whatever is stored in that D memory stage. So that's what is happening now. So this was the entire code for you guys. A proper walkthrough and possibly a demo. Also, I gave you a demo how changing these numbers works. So if you change 20 to 30, it's going to calculate multiples of 30. Finally, if you change this number 100 to some other number, example, I showed it to you when it was 21, the simulation just says failed in the logs. Right now it's going to say it has reached max number of cycles because I haven't compiled it. If I go ahead and compile it and check the logs, it says simulation passed, right? Because 100 is present in the multiplication tables of 20. So yes, I think that is it for the demo and explanation. And that was my entire project. So this brings the session to a close. Are there any doubts for me in the chat, which I can take up quickly? Hello? Hello? Is anyone there?
Yes, sir.
No, are there any doubts for me in the chat? I think I can close the session now. I've explained whatever I had to do with this. So if there are any doubts, I can take them up.
Yeah, so we have one question. So like how precise our design will be on maker chip compared to actual implementation on FPGA?
Okay, for that question, how do I even answer? Like, of course, there's online sandbox and what's happening in the background, you actually don't know that. It's just providing you with an HDL where you can edit your information. But if it might be that this is just a hoax, right? You can never know. But obviously, to get something to implement it in this way, it's not hoax because one thing is you have very generalized and or operations, right? And it's going to work for any given ISA. So depending on how you decode and things, so it's a pretty legitimate design. As I told you, I've not tested it on a real FPGA board already, but yeah, it should work fine. I mean, it's giving you the SV files as well. So just a matter of someone going ahead and burning this code onto a board and checking it out. But since I've not done that, I cannot comment on it, but it's a proper pipeline. And I mean, whatever code you write makes sense. And when it comes into this, actual module level design, it actually makes sense. So I would say it's pretty legitimate like that.
Yeah, thank you, sir. The next question is Verilog used in mobile chip making?
Ooh, these are not questions for me. These questions I cannot answer. I've not even looked into this. So yeah, I mean, I was just going through this instruction set architecture course, ISA course, and I just know the computer science aspects of the things. The EC stuff and things I've not yet looked into those aspects. But yeah, I just know this, how to code the data path. If there are questions for this, then I would very happily take them up. But I mean, all these systems which are also being designed are used to build SoCs, right? And SoCs are systems on chips, and that's what all your mobile phones are running on. So yeah, if in that sense, I am not a technically qualified person to answer this, but I think the answer to your question is yes.
Thank you, sir. So there are no more questions in the Q&A.
Yeah, then.
Thank you.
Then I would end the session. Thank you to everyone for listening, being a proper, very, very disciplined audience. And that's it. We can go ahead with whoever the next speaker is, or if there's a break, those things can happen now.
Yeah, thank you, Ishan sir. Thank you for the wonderful session. And thank you all the participants for listening and putting your queries. So thank you, everyone. So we have ended our first session of today's class. So our next session will start from 1 p.m. with the same link. So before you log out, so I have a few announcements for the participants. The first thing, the slides for day one, that yesterday's session has been posted in the Drive link. So you can visit your Drive link and check the slides of yesterday's session. The second announcement is that your attendance for day one has also been updated, and in the link to check your day one attendance is also posted in the Drive folder shared with you all. So I'll request you all to kindly check the Drive folder to check your attendance as well. And some of you have not joined using your registered email ID. So I would request everyone to please note that it's quite difficult at our end if you do not register, if you do not log in with a registered email ID, because out of around 450 participants, if we get to search each and everyone's name, so it's quite difficult for us. So for yesterday's session, you have been marked present even if you have not registered with your email ID. But from today's and tomorrow's session, those things will not be considered. Attendance will only be marked only for those who log in with their registered email ID. And Rahul Panwasa, yes, the sessions are being live streamed on YouTube as well. And the YouTube link is also been shared in the Drive folder. So for your attendance, you have to attend the live sessions in WebEx only. Yes, but for reference purpose, you can see the YouTube. And the YouTube link has been provided in the Drive. You can check that. Yeah. And the third announcement is that from tomorrow onwards, we'll be using the Cisco WebEx meeting application. We'll not be using the Cisco WebEx event, as some of the speakers are facing some technical difficulties using Ubuntu in Cisco WebEx event. So from tomorrow onwards, we'll be using the Cisco WebEx meeting application, and we'll share with you the link for tomorrow's session. After today's session ends, you will be getting the link of tomorrow's session. I hope I made 3 announcements, and I hope these all things are clear to you. The first announcement, I'll repeat once again. The first announcement I made is that the yesterday's day one course materials have been uploaded in the Drive folder. You can check. The second announcement is that your day one attendance has been updated, and the link to check your day one attendance has been updated in the Drive folder. You can also check that. And this is to also inform you that these sessions are live streamed on YouTube, and the YouTube link is also been provided in your Drive folder. So even if you miss some part of the session, you can again revisit through the YouTube link that has been provided in the Drive folder. And from tomorrow onwards, it's a request to all of you to join with your registered email ID only. As for day one, it has been considered, even if you have not joined with your registered email ID, it has been considered and your attendance has been marked. But from tomorrow onwards, so it's very difficult at our end to check. So it will not be marked. So kindly note that you register with your email ID only. Okay, and from tomorrow onwards, we'll have the session in the Cisco WebEx meeting application, and the link for the same will be shared with you after today's session end. So with this announcement, I'll be stopping here, and we'll have a break now, and we'll start the second session from 1 p.m. So I request you to kindly get joined again by 12:45 p.m. if you get disconnected, and if you want, you can stay connected and you can continue. So thank you all participants. Thank you Ishan sir, thank you Abhinandan sir, and thank you E&ICT team for the support. Hello, Abhinandan sir. Hello, Abhinandan sir. Hello, Abhinandan sir. Good afternoon, all the participants. So we are waiting for a few more minutes till all the participants join. We'll start in few minutes. So even if you know your friends, so please ask them to join. We are starting the session in few minutes.
Hello, everyone.
Hello, sir.
Hi. Yeah.
Yeah. So Arjun sir, yes, right?
Yeah. Yeah.
Okay. Okay. So,
Abhinandan, are
shall
you there? I just shared the PPT.
I'm there. I will share. I will share. I
Sure,
thought
yeah.
Venkatesh should be joining. It's okay. I can share. Not an issue.
No problem. Either case, if it is.
Venkatesh sir has also joined, but I guess he joined with mobile phone. He is in the panelist, but he
Okay.
joined with
So
mobile
anyway,
phone.
you can see my
Yeah.
screen, right?
Yes,
I
sir,
can.
yes,
Yes.
sir.
Yeah. Okay. Fine.
Yeah. Okay. So, good afternoon, all. Good afternoon, all the respected speakers, our coordinators, and participants. So, today's sessions will be taken by Mr. Arjun Harinak, sir. So, on the topic VLSI. So, Mr. Arjun Harinak is a design verification architect with more than 12 years of experience, industry hands-on experience on system Verilog and VHDL, UVM, that is Universal Verification Methodology, industrial research scholar at JNTU Annathapuram in the field of usable system-on-chip verification methodology. Designed and developed multiple system-on-chip level test bench architecture for complex designs. So with this small introduction of Arjun sir, I request sir to kindly take over the session.
Thank you. Thank you. Thanks for that quick intro. So I will be talking about a few of the initiatives that we have taken up at JNTU Anantapur, where in collaboration with Open Power Foundation, right, they have been developing a few proof of concepts and a few of the fabless products, I would say fabless system on chip, right? So I've been interacting, I've been coordinating with the team at JNTU Anantapur, understanding the kind of infrastructure for the front-end perspectives to design a fabless system on chip, right? So as you all know that the ingredients or the components that constitute an SoC would be a processor, bus, and a few peripherals. When I say peripherals, they can be functional, they can be memory controllers, they can be high-speed serial data interfaces, right? So constituting all these, right, connected to a processor core via interconnect or a bus, you will actually have a system on chip that is agnostic to your domain, right? So understanding the availability of the open source cores like A2I, A2O, and the availability of the processor cores and the interconnects and a few of the IPRs from the open source, from the Open Power Foundation platform, right? So we developed a fabless system on chip, and the name of it is Anant, right? So I will be actually talking about it for the next few minutes, which will take you through the design flow, design and development flow. In fact, the size of the design, what does the design constitute of, how is it that we are trying to utilize the open source core and the open source ISA and things like that, you know, all those perspectives will be discussed moving further. Yeah, next slide, please. Yeah, so as I mentioned, this is actually done in collaboration with Open Power Foundation. So I did mention that this is actually a domain agnostic system on chip, but specifically this point in time, Anant is actually developed with a few peripherals that would target the execution of an IoT application. However, this is predominantly to serve the academic R&D purposes at this point in time, right? But we also have a few peripherals added in such a way, and the customization is done in such a way that moving further, if there is any custom IP addition, that can be easily mapped, right, in terms of the core addition or the address mapping, that can be very easily done. That the kind of the plug and playable perspective is what we brought in to this fabless SoC. Go ahead, please. Slide. Yeah, so the kind of roadmap that we have, right, for the next 3 years or so, because we have started it now, we wanted to have a first cut, fabulous system on chip at the first place with the design in place. But the actual idea is to have a core SOC which will serve the purposes of all your real-time perspectives. When I say IoT as such, really, that can actually go live in a silicon die. That's the plan. At this point in time, we wanted to come up with a fabulous SOC that can be converted into a netlist, and we wanted to come up with a prototype, an FPGA prototype initially. But if you see the roadmap initially, the proposal, that is what we have started, what all ingredients or what all peripherals that would constitute of. And then we wanted to come up with a verification architecture. So let's say if we wanted to kind of commercialize it in the future, or if you wanted to open source, forget about the commercialization, but even if you wanted to open source this, see, it should be available as a whole package, right? The SOC along with the validation platform should be made available. So we thought the VNV platform, which constitutes the UVM based, SB UVM based, system Verilog UVM based platform, which includes the verification IPs that are hooked up to the respective peripherals, along with the system level test bench is also expected to be made available as part of your Anant 1.0. And we also wanted to integrate a few more peripherals with respect to the performance analyzing block, or bringing in more of the real-time perspectives. And finally wanted to port it on an FPGA once the design is kind of freezed, right? And we wanted to showcase it on a FPGA as a FPGA prototype. So that's the kind of roadmap that we have set at this point in time. This is subjected to a few changes based on the availability of the resources and kind of enhancements with respect to the peripherals we have chosen, right? So tentatively, this is what we have as far as the roadmap is concerned. Yeah, go ahead, please. So from Open Power, we actually have access to 3 different open source cores. One is A2I, A2O, the in order and the out of order power processor cores. And we also have access to microwatt. But for this particular SOC, we thought A2O could be a good match. The out of order processor core, which is actually compliant to the AXI4 interconnect, the bus architecture. In fact, all the peripherals are also designed, right, are made compliant to the AXI4 bus architecture. And so the peripherals, if you see, are SPI, I2C, PCIe, Ethernet, DDR3. So SPI, I2C, PCIe, Ethernet will be serving as the peripherals for the data connectivity ingress and egress, right, from the outside world within the process for the processing within the chip, and will serve as a high-speed serial data interfaces. DDR3 and flash like NAND NOR will serve the purpose of the high-speed memory controllers to cater the needs of the memory applications. DDR approximately can capacitate close to 2 GB, whereas NAND and NOR approximately to 1 GB each. So that's the kind of the composition we have. And as far as the functional IP is concerned, it is DMA. It's not just DMA, it's a scatter gather DMA that we have as an IP here. So that will be part of the functional IP perspectives of the SOC. Yeah. And as I mentioned, this is an AXI compliant interconnect, right? So all the peripherals are connected to the processor core to AXI. Yeah. Next slide, please. So this is the overall architecture. So this is the pictorial representation of the SOC that I've been talking about. We have an A2I, A2O core where we have some local memories. As you understand that your SOC comprises of 3 different memories, right? From the basics, you'll have an L1, L2, and L3. L1 is something which is directly memory mapped to your processor, which serves as a local memory, right? So where you don't have a base plus offset composition. All the address locations by default becomes an offset to be accessible from your processor. So that's your L1. Generally, IRAM and DRAM will constitute out to be your L1 memory. And when it comes to L2, it is still within. So L1, L2 comprise to be the on-chip memories because they will be available within, within the address map of your processor core. But however, the difference between L1 and L2 will be like L1 is a directly mapped where the composition of base plus offset constitution will not come into the picture. Everything will be offset. But L2, though on chip, will have the composition of base plus offset is equal to absolute address because that is accessible through your bus, where controller is not required because that is still within its on chip. So that's an L2 memory. We thought for internal, we thought there could be a situation where your application binary would cross the L1 capacity. At this point in time, it is 32K of your IRAM DRAM composition for the A2O core, which will sufficiently accommodate the size of any big application. But just to make sure that if it is not running out of the memory and to accommodate the flow controls, we thought L2 would be handy, right? So we also have an L2 memory made available as part of your internal SoC architecture, and you can also see the other peripherals that I mentioned in the earlier slide pictorially captured, and they're mapped address wise as well as the physical mapping is concerned through the bus to the processor core. So this is the quick representation of the overall SoC. Anand, thank you. The next slide, please. I was actually, so for the next few slides or so, I will be talking about the way in which all the peripherals are designed and developed, right? So we have a team which is actually working individually on each and every peripheral development. As I mentioned, SPI, I2C, PCI, Ethernet, DDR, NAND, NOR, and DMA, along with the XC interconnect. So we have one engineer assigned to the development activity from the scratch, looking at the specs, right? So we have the development activity happening in Verilog. So all the subsystem components of each and every peripheral are carried out from the scratch in Verilog, where the integration and the connectivity of the subsystem level. And as I mentioned earlier, this is actually made, all the peripherals are made compliant to the AXI. So the AXI part master slave compositions as per the protocol, as per the peripheral connectivity are also made available. So for all this, the backbone, I would say the connectivity backbone, the interconnect will be AXI, right? AXI4. So just to quickly give you some perspectives of AXI, first of all, your A2O core is actually compliant to AXI, and the AXI is actually made compliant with respect to the 16 AXI4, where the 16 number of maximum masters that can be accommodated within one connect of the peripheral processor interconnect, and the maximum number of the address range in which it can capacitate is 4K, right, with the address boundary. And at the same time, a few of the log and the prod protected instructions are also enabled only to ensure that the authentication and authorization is in place for the data access coming from any external peripherals. So that's pretty much about the AMBA XA4 and how it is actually designed and developed. And in fact, all the read and write transfers are designed in such a way, like for example, if it is a memory, so you don't have the configuration of a master coming from your memory controller, right? So it is always a processor which becomes a master. So it is a slave core that is designed and a slave wrapper from the master, from the memory controllers like DDR, NAND, NOR, for which the AXI is actually designed. So where the AXI slave connects or communicates with the master of the peripheral of the interconnect. Likewise, all the peripherals also. PCI Ethernet supports the full duplex transactions, right? So there is a master as well as a slave interface that is made available for this high-speed serial interfaces. If it is not required, then it is only the slave, because the master by default becomes your, the processor core by default becomes your master that will initiate the write and read transfers. Next slide, please. So PCIe, just to talk about the PCIe core, it is made available as an endpoint. As you know, PCIe generally has three different configurations: endpoint, root complex, and a switch, right? So this point in time, we have chosen PCIe as an endpoint EP. Coming to the speed, it operates at 8 giga transactions per second. PCIe 1, Gen 1 is 2.5 giga transactions per second. Generation 2 supports 5 giga transactions per second. PCIe 3 is about 8 giga transactions per second. So that's the kind of PCIe core we have chosen. And the support to the external PCIe to the root port is via pipe. Pipe stands for PCIe physical interface for PCIe Express. So that's the kind of composition the PCIe core has got. And when it comes to the scalability, it has got 4x of the scalability connected to the root port or to the root complex. In general, as I mentioned, PCIe is actually a full duplex protocol. Not only the processor core on the SoC front, right? So it will also be a root port that is capable enough to generate configurations acting as a master. So the PCIe core, the CXPL core is what you name it. Actually, the PCIe will have three different layers. One is the physical layer, next is the data link layer, and the transaction layer. So EP to RC, endpoint to root complex, or root complex to endpoint. So the transaction happens across these three layers. So the file layer, the actual physical layer is actually designed in such a way that the electrical characterizations and the mapping is in line with the pipe, all right, of the 4x scalability that I spoke about. So we are actually coming up with VIPs for all these peripherals, which will mimic the real-time scenarios and validate functionally these IPs, because this is more on the fabless part. So all the cycle accurate simulations will be carried out during verification, which I will be talking about in the next sessions probably. Yeah, next slide. So I2C and SPI, both of these peripherals are actually used for both authentication, authorization, as well as for low speed data transfers whenever are required on ad hoc basis. And I2C, SPI both are actually required to cater the IoT based transfers on most of the occasions. If you see the IoT based compute loads, majority of the transfers are catered on buses like I2C and SPI, which ensures some node-to-node connectivity. When I say node, it's a device, right? And one additional advantage that we will have, unlike the other high-speed serial data interfaces like PCI Ethernet that comes with I2C SPI, would be the data transfer which starts with authentication and authorization, whereas PCIe I2C kind of a protocols will have a data transfer upon enumeration, right? So there is a difference upon enumerating a device and performing the data transfer, authenticating and authorizing a device upon a data transfer. So that's the difference, right? So you will have, for example, you take a protocol like Bluetooth, right? It doesn't actually do any protocol transfer, data transfer, but the data transfer will happen only after the authentication, where there is a passcode coming from both the nodes, and if the pairing of the passcode happens, only when the authorized peripheral will be allowed to perform the data transfers and for the processing. So such kind of authentication and authorization post data transfer is supported by I2C and SPI protocols, which made us to choose these protocols made available as part of this SoC composition, right? Yeah, let's go to the next slide. Maybe SPI you can skip. There's nothing much because both will. Yeah, next slide. Yeah, so DMA is something which we have actually worked a lot to see that the composition of it is made in such a way that it reduces the overall the overhead on the processor core. In fact, this is got of prime importance to see that the performance metrics of our SoC are most optimal. For example, if there is an urgent operation in which your processor core is doing, right? Let's say if the request is actually coming from another peripheral where the current transaction is already locked between your CPU and, for example, Ethernet. In between, if it is a PCIe which is requesting access of a processor, and the arbitration at this point in time for this application will be carried by the SC. What happens is the address maps of all the PCIe will be hardcore. If an inter comes in the state, your processor to halt its operation, right? You generally understand the perspective of the perspective of source the address of the next instruction. The stacker will hold the address of the execution.
Arjun sir, sorry to interrupt. Hello, Arjun sir. So sorry to interrupt. So your voice is breaking.
Okay. Okay. One second. Let me. How about now? Am I?
Yeah.
Out and clear?
No, sir. Like
Okay.
Again, it's.
So it is breaking, is it? Okay.
Now it's fine.
Okay. That's how it goes. Let me know if it is still breaking. Let me continue as of now. So DMA, as I was mentioning, so in case if there is an interrupt that comes from any of the other peripheral in the SoC, the processor core has to pause its operation and will have to buffer the SPPC values at a place, and with the help of an ISR, interrupt service routine, will serve the interrupt and then will come back to the SPPC where it has buffered, and then will continue with the operation it halted before serving this interrupt. So this actually requires a lot of processor cycles to be consumed, right? So which in turn will increase the latency, adds up to the latency, and will effectively decrease the overall throughput, efficiency, and bandwidth of your SoC, overall SoC, as well as the processor, right? So which is not good, right? So you are always looking at a faster computing as well as an efficient computing with optimal performance metrics. That's actually what you're looking at. In lame terms, it is not only a better readability. For example, if a code is, it is also looked at the faster execution. So DMA at this point in time that we have chosen is a scatter gather DMA controller, right? Where it will be holding the configurations of all the peripherals that are made available in the SoC, apart from the DMA and the processor core, right? It will hold the address locations. It is actually holding the addresses of all the base plus offset compositions. I mean the absolute addresses of all the peripherals, SPI, I2C, DDR, Ethernet, all the controllers within its within the DMA, where if the interrupt comes, the processor will not will not request the ISR to serve the purpose, but it will actually direct it to DMA, which will actually cater the request and complete the processing of the request, right? So that in turn will reduce the latency and will reduce the overhead on the processor core and will have a significant impact on the performance metrics of your SoC. Yeah, next slide. So both NAND and NOR flash controllers, as I said, accommodates close to 512 to 1 GB of memory. See, the predominant purpose of having the NAND and NOR flash controllers on any SoC or any chipset is, see, you perform the booting of your processor core either on chip or off chip. Sometimes what happens is, see, we understand that we are at the era of IoT, AI, ML kind of workloads, which are quite data compute intensive, and at the same time, the application binary that gets generated for such kind of data compute intensive applications is quite huge. Okay, so if it is L1 booting, so you generally do an L1 booting or L3 booting. L2 you generally don't use. L2 as I said is on chip, but connected through your processor core and bus, connected to processor core through bus. IRAM and DRAM, right, are the ones I am talking about when I say L1. See, 32K is what I said, right? So let's say if it is a situation where the boot data, generally your instruction RAM is undisturbed, right? So you will never ever perform any application executions or the application boot data from IRAM. It's always the DRAM. Let us say for that application execution of any peripheral, right? That if the such application is crossing the 32K space of your DRAM. When I say application data, that includes the boot data. So the boot plus application code, right? There are a lot of situations where for workloads like AI, IoT, ML, that this 32K might run out of will be insufficient, right? So at that point in time, you definitely have to go for a memory option that can capacitate the application binary for boot as well as the peripheral access, both. So at this point in time, we thought NAND and NOR could be the best options, though we have QSPI kind of other flash controllers also. Understanding the kind of workloads that this particular SoC might cater in the future, we have chosen NAND and NOR flash controllers, and the development activity, as I mentioned, is done from the scratch for these two peripherals. And the memory controller specification is considered from JEDEC standards as well as from Lattice Semiconductor, where the subsystem level FIFOs and the AXI is independently developed. As I mentioned, these two are memory controllers. It will have only the slave component of the AXI, but the FIFOs and the other register layers are all developed looking at the JEDEC specs of the NAND and NAR flash controllers. And for the performance, we have considered the benchmarking of the Lattice Semiconductor specifications. Yeah, you can go ahead. Yes. So Ethernet, the purpose of having Ethernet in this particular SoC is to perform the packet processing applications, right? So the ingress and egress of the networking perspectives. Well, for example, if it is a TCP IP packet that comes from an external world, so there should be an interface which would support the ingress and egress of such packet data. So we thought Ethernet would be the best choice. So this is actually configured in GMII, which will connect to an RGMII from the external world for the packet ingress and egress, and will cater the needs of the packet processing applications within the SoC. Outside of the SoC, I mean both on chip and off chip is what I'm trying to explain. And this is actually configurable Ethernet, which is compliant to the 802 Project 802 standard. And the kind of support that we have got within this Ethernet is packet classification, routing, queuing, which can actually be scaled up to the switching and routing performance. So overall, we are looking at, for example, 10G of the overall performance, right? So this can be scaled accordingly, and such kind of a configuration parameters, configuration options are made available within Ethernet. And as I said, this will support the full duplex operations, and it is made compliant to AXI. Since it is full duplex, we have both master and slave configurations developed as part of this Ethernet. So there will be master core slave connecting to the slave master cores coming from the AXI interconnect from the processor core, and within we have some flow control flow control subsystem blocks along with the FIFOs and the GMII blocks, which constitutes your actual core of the Ethernet, connected to the RGMII of the external world. That's how we have the Ethernet is concerned. Yeah. Next slide, please. So DDR, actually, see this particular memory controller is developed considering the JEDEC standards, which is again an open source standard. Unfortunately, we have not considered any performance benchmarking perspectives for the IP that we have considered. So for this, thorough verification will be carried out with the perspective of performance metrics also. From the scratch, all the development that we are doing for DDR will again require a thorough IP validation, either in system Verilog or UVM at an IP level, at a standalone level is what I'm trying to explain. So the DDR at this point in time is can capacitate close to 2 GB of memory. The idea is actually to make it compliant to any of the vendor specific memories. So generally you will have Denali kind of memories that are compliant to your DDR controllers. But the way in which we have designed this is it can actually it can actually be made compliant to any of the memory that can adhere to any memory protocol in general. For example, the busy, the ready signal compositions, all the address data control responses, right? That are part of your DDR. If you have a memory that is compliant, your DDR can be used to plug and play. That's the kind of composition that we have when we developed when we have actually developed this particular DDR core as a controller, right? And the purpose of having DDR is another thing that I would like to explain here. See, apart from the boot, apart from the application code that can overflow, we've also wanted to have additional data for high-speed data interfaces. For example, you consider this PCIe as an endpoint, right? But in general, if you take a root port, right, a root port, there will be a huge memory that capacitates around 3 to 4 GB of data that can cater the needs of application processing, boot, as well as your subsystem level packet processing application. So there should be a memory that is faster to cater all these three needs, along with the support to connect to a root port as well as an endpoint. So that is what made us to choose DDR3 along with NAND and NOR controllers. As you also know that DDR, the composition of the memory is more in terms of banks rather than rows and columns, which becomes the pointer access delayed because it is sequential, right? But at a bulk, at a stretch, to perform some burst transactions for all these high-speed data transfers, DDR is the best option, right? So that is another reason which is made us to choose DDR as one of the peripheral for our SoC. Next slide. So as you know that your fabless IP, right, will have two phases. One is an EDK phase, an embedded development kit phase, and an SDK phase, software development kit. So the processor comes along with an open source ISA core as well as an SDK, right? That will come along with a composition of a compiler, assembler, disassembler, cross compiler, linker, loader, and scheduler. So whatever C, C++, or whatever the high level language application that you develop will be given as an input to this SDK, which will yield an ELF or a binary, which will be fed again as an input to your processor core. That can be a backdoor access, or that can be a processor based direct access also. Irrespective of that, the overall SDK is in place. So the final demonstration that we wanted to, so whatever I spoke about till now before this slide, that talks about the embedded development kit phase, the embedded development or the hardware embedded development, EDK development, all right, which involves Verilog, SV kind of development, integration, and things like that, right? But if you look at the software stack, right, you will have hardware beneath everything, bottom up. Then you have OS kernel. On top of it, you will have a driver. On top of it, you will have an application. On top of it, you will have the user. So that's the way in which your user will access the hardware. So these are all the intermediaries that I spoke about. So the SDK talks about the other layers, the driver, the embedded flow is all embedded software flow lies within your driver development, the OS kernel porting, and the application development. All right, so we have a composition of both, right? Because we have all the SDKs available coming along with the A2O core. So the final demonstration is both on the simulation platform or on the FPGA that we wanted to prototype. We'll have a C code or a C++ code given as an input, like I mentioned just before a couple of minutes, to the SDK, which will yield an ELF binary. Again, fed as an input to the simulation platform or the FPGA prototyping platform, will access the respective memory and perform the write and read operations. That's the kind of demonstration we have planned. That diagram we don't have at this point in time, but yeah, that's the overall composition our particular SoC has got as far as the demonstration is concerned. Yeah, next slide, please. So quickly, this is what we wanted to kind of showcase. What is it that we have been doing for the past few days? Just to talk about the next steps, because this is predominantly talking about the design and talks about what we have done till date, right? Moving further, we wanted to develop the VIPs, the verification IPs for all the peripherals that we spoke about. Dr. Abhinandan, can you go back to the SoC architecture slide for a couple of minutes, please? Yeah. So this is the design. This is actually going to be the design. On top of this, there is another team which is actually developing the VIPs for all the peripherals that you see, and is also developing an SoC test bench that will encapsulate or instantiate the design that you see on the screen now, right? So along with this, there is another team which is actually developing, right, the drivers for all these peripherals. So whenever there is a device, you need a device driver to access it, whether it can be a hardware platform or it can be a simulation platform. You need a driver, right? So all the address mapping perspectives, all the write read functions targeting the respective addresses. And when I say address, it is absolute address, which is equal to the base plus offset. Each and every peripheral will have your base plus the offset is the composition of your base into multiple address locations, right? So all that will be done from the high level driver codes. So we have the VLSI, the MTech VLSI electronics and communication department, MTech VLSI guys, and the digital system computer electronics guys developing the hardware perspectives of it. When it comes to the drivers and the OS porting, we have the students coming from the PG background of School of Computing, the computer science engineering department, right? So this is the next phase of this development. And finally, as I mentioned in 3.0, the third year, we wanted to port this on an FPGA, and this will be available as a whole package, right? The SoC with the verification database as well as the verification platform for all the peripherals and the driver. So this will be an all-in-all whole package that will be made available in the next couple of years. So that's pretty much about it. Thank you. I think I will leave the session for the questions, and I'll be happy to answer any questions you have. Yeah. Are there any questions?
Yes, sir. So we are having one question like, so how have you implemented these protocols or peripherals?
Yeah. Implementation is done using Verilog. So we have considered specs for all the peripherals. We have used we have actually used open source standards, right? We have used open source standards like JEDEC, for example, for all the memories, and open source compute platforms, open cores, and few of the specs are also available from the open source compute platforms like Linux Foundation, Open Power, RISC-V kind of open source communities. So looking at all these open source options, we have collected the specs and we have kind of developed all the peripherals from scratch in Verilog. and we have integrated them within our simulators. Fortunately, the university has access to all the utilities and infrastructure. For example, Model Sim, Questa Sim from Intergraphics, Vivado from Xilinx, and physical boards were also available there. So utilizing all this infrastructure and the open source compute platforms and the specifications, we have developed all these from the scratch in Verilog. And implementation, yes, as I said, we wanted to come up with an FPGA prototype, right? We will be porting it on an FPGA, and at this point in time, we are looking at a couple of options. One, a Xilinx FPGA, and an Ultra, I mean, which is an Intel FPGA, both. We wanted to explore those options, but the implementation, as I said, will be part of the third-year roadmap. But still, the architectural explorations are still in place. Since they are open source standards, what kind of modifications are needed for implementing in Verilog? No, absolutely not. See, any source code, that you wanted to develop requires a problem statement, and the problem statement is the protocol itself, right? So it is Ravindranath who is asking this question. Hope this answers your question. So it's all the problem statement that you need, and you need to convert it to code. So in Verilog, as you know, you will have to define a macro architecture, subsystem level component level diagram. Then you will draw an FSM, finite state machine, right? And from the finite state machine, so basically FSM will give you two things: output and the transitions. Transitions will talk about the control path. Output will talk about the data path, correct? So combining these two in Verilog, right, you will have the overall code of your system. So all the subsystem level blocks, right, connected together will give you the actual IP, the final IP. That's how we have implemented in Verilog. No modifications are required. We also have a question from Sivaramakrishna. Do we need individual verification IPs for each of the peripherals, or a single IP sufficient for? No. Single IP will not be required, because there are multiple IPs acting as peripherals, right? Ethernet is one IP, SPI is one IP, PCI is one IP. So see, it's very simple. Well, it's like this. You assume that you are purchasing a mobile phone, okay? If you see your mobile phone, your mobile chipset comprises of, physically when you see, you will have different interfaces. Touch is one interface, that's one peripheral. Your USB charging C-type or mini, whatever it is, that is one interface. Your SIM card is one controller. Okay, your memory card is one controller. Okay, your 1.5 mm jack, audio jack, that is one controller. So what do you do actually? See, you can't use USB to verify all these, correct? You will plug in 1.5, you will use a headphone, you will take a headphone, you will plug in the 1.5 jack and see whether the audio is coming out. So you are using a 1.5 mm audio jack for a male pin to connect to the female pin of your mobile phone to see whether it is working. Likewise, you will use a USB C-type male pin connecting to the female pin to check whether. So the answer to the question is, one IP will not be sufficient. Multiple IPs compliant to their own protocol are required to verify each and every IP of your SoC. This is a chipset comprising multiple peripherals. So the respective protocol VIPs are required to verify the respective design IPs. As simple as that. Okay. As a researcher, where we have to start? Okay, so as a researcher, I would say this is one area. This is a question from Shivam Gulati. I think this is a very good question. So first of all, Mr. Shivam, the point is, VLSI itself is a very niche area, right? And being niche, there is a lot of scope for research, first of all. Unfortunately, the point of fact is, India, we have a lot of institutes, including the institutes of national importance and the premier institutes like IITs, NITs, IISs. Not many are actually, I'm talking about VLSI specifically, right? Not many institutions are having the syllabus that is actually matching to the industry needs, right? That is one more thing. And I'll tell you why. I'll actually tell you why. See, most of the courses target your CMOS VLSI design, your analog part, your not much of the digital perspectives matching to the real-time applications at this point. For example, system Verilog. See, when you take VLSI, the perspectives start from your transistor level, right? Next from transistor to gate level to device to system to application. This is the composition if you see the hierarchy. Most of the study that you do, including your UG, PG from all the premier institutes, as far as my knowledge is concerned, right? It is more at a transistor level or your gate level, right? You talk about NMOS, PMOS transistors, you talk about the pseudo NMOS or the PMOS compositions. So that's all good, that's all okay. But actually your device level composition, your SOC, I can see some of the institutions and the universities having SOC as a course. See, I'm actually talking about MTech specialized courses like MTech in VLSI, MTech microelectronics, things like that. That is unfortunately not there, right? So having said all these things, answer to your question, the scope of research is more at device level. I think the transistor level, as far as my understanding, I'm not sure if the participants of this call are from a VLSA background who are PhD holders also, but as far as my understanding is concerned, there is a lot of work which is already done on the transistor and at gate level. But I think there is a lot of scope, right, for research, for R&I, research and innovation at a device and system level. So in that perspective, I would say you should explore where you will have a lot of chance to learn and then come up with an innovative idea there, right? So that's my input to you. Can we implement, Chintan Patel has asked a question, can we implement deep learning applications with SOC? Like, yes, absolutely, we can. In fact, see, each and every peripheral that I'm talking about is one IP. So that is connected to your processor core via interconnect. So you're talking about zinc SOC. Fortunately, what happens is, Chintan, your zinc board comes with an ARM core, which is a CPU that is hard macroed on the board. And fortunately, you will have an AXI interconnect, that is AXI fabric is what you call on-chip fabric, that is also available on board as a hard macro. So you will have a PSPL architecture, right? PS is a processing system which is a fixed logic. PL is a programmable logic, where you can port your own IP, fabless IP, which is synthesizable. You can generate a netlist bitcode and burn it on the PL side. That will be memory mapped to your processor code. That IP can be a deep learning IP also. For example, there is something called as DPU, Deep Learning Processing Unit, which is an IP from Xilinx. That will actually be mapped on the PL side, but that will be connected to your ARM core. So that becomes a co-processing unit. So a CPU plus DPU will help you to cater the deep learning loads. Okay, Shailesh Chandra Pandey has asked a question: how verification, SOC verification is done by writing C test cases? Okay, see, as I said, your SOC will comprise of a processor core, right? And the processor will be connecting to multiple peripherals through bus. See, you will not be applying the inputs at pin level to your processor. You will actually, what does a processor have? Processor has got a compiler, right? And a processor will always accept a high level code, not a HDL code. You understand this? HDL is a hardware description language which is used to apply input at a pin level, right? But HLL, high level language, is a language which is actually written even above your mnemonics, even above your machine level code, which comes in between, an assembly code basically. So that is something which your processor core accepts, right? So what you do is you write your application codes for, basically your application code will comprise of the configurations of your registers. You access the register abstraction layer of all these peripherals, where the memory map is made available or else it is made visible to your processor core, and the addresses where I was mentioning as absolute address, which is equal to base plus offset. Okay, so that addresses are made available from your application code, which is in C++, high level code, and the configurations to this particular registers are made available. That particular code is given as an input to your compiler. That will in turn generate a binary, right? Not just a binary. In fact, it will also yield another output called disassembler file that will talk about your SPC, pointer and program counting events. However, that binary will be given as input to your IR instruction. The calculations of the respective peripherals are done. That's how it is going to be. Right? So that is why you write C test cases to verify SOS verification. We also another question: the past research I want to study the material. Okay, I don't know how I can answer this question. I think you have to. Yeah, there's a lot of research. There is a lot of literature survey that you have to do at a system level, Shivam, to understand what kind of scope you have. And first, finally, what we include from SOC architecture. See, SOC architecture, we conclude what kind of peripherals we have and what kind of an applications will it cater, and how can we kind of improvise performance metrics and things like that. Ishad Ali, how can we develop FPGA-based programmable logic controller that can communicate between PC and sensors? See, it's very simple. Okay, answer is pretty simple and straightforward. So all the PC generally, right, that will connect to your FPGA through PCI cable, right, or UART also sometimes, or some USBs also these days. Or you can go for Zinc boards which come with PSPL architecture. The host machine becomes your ARM core. Anything is possible. Sensors, all the PLCs, they come as Verilog codes, for example. Okay, you need to take that Verilog code, generate the netlist, create the binary, and burn the image file on the FPGA. So that is a memory map to your CPU, and that is how you will be able to establish the connectivity between your PC CPU and the sensor IP. That's how it is going to be. I also have a few more questions. Have you implemented these protocols? Okay, I've answered it. Okay, I think these are all the questions I had. Looking at the Q&A, verbally, if there are any other questions, I'll be happy to answer. Otherwise, we can probably wrap up the session. Yeah, Abhinandan and the EICT Academy from Guwahati, the host. Am I done? Then if there are any other questions which are not visible to me, kindly let me know. I will be happy to answer them.
Yeah, no, sir. So almost all the questions are being already addressed. So there are no questions left. So
okay.
Yeah.
Thank you.
Thank
I
you.
think that's pretty much from me. Hope the session was interesting. Thanks for patiently listening to me. You all have a good day. Thank you. Thank you, Abhinandan.
Yeah.
Thank you, Arjun sir, for the wonderful session. Thank you all the participants, and thank you, Abhinandan sir, for the coordination. And to all the participants, so a separate Google WebEx meeting link will be sent to you by today. So the link will also be shared in the Drive folder and to your registered email ID and in the Telegram group as well. So from tomorrow onwards, do not use this link to join. Use the Cisco WebEx meeting link that will be shared with you by today. Thank you. Thank you, Arjun sir. Thank you all the coordinators, and thank you participants for joining.
Thank you.